There is something in our galaxy that controls the motion of 400 billion stars, something invisible, something so dense that light itself cannot escape. And it sits just 26,000 light-years from the chair you are sitting in right now. Its name is Sagittarius A star, and for decades we knew it was there only because of what it did to everything around it. Stars whipping through space at 17 million miles per hour, entire stellar systems bent into impossible orbits, a region of spacetime so violently warped that the fabric of reality itself behaves like liquid glass. All of this happening around a point in space we could not see, could not photograph, could not directly observe in any meaningful way. 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, a supermassive black hole sitting at the exact gravitational center of the Milky Way, holding our entire galaxy together through sheer gravitational dominance. And until 2 years ago, every image we had of it was a guess, an inference, a mathematical shadow cast by things we could see being destroyed by something we could not. Then, in April 2022, the Event Horizon Telescope did what most physicists thought was functionally impossible. It captured a direct image of the event horizon itself, the point of no return. The boundary where physics, as we understand it, begins to fail, where time slows to a crawl, where the rules that govern everything else in the universe quietly step aside. This is the story of that monster. What it is, how it holds our galaxy hostage, and what happens when you approach the one place in the universe where even light cannot run fast enough to escape. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a point in space, roughly 26,000 light-years from where you are sitting right now, that you will never see. Not because it is hidden behind something, not because your telescope is not powerful enough, but because light itself, the fastest thing in the universe, the one universal constant that defines what it means for anything to be observable, stops at its edge and falls inward forever. And yet, despite being invisible, this object controls the motion of 400 billion stars, including ours. You are orbiting it right now. So is the Sun. So is every planet, every comet, every speck of dust in the solar system. We are all passengers on a cosmic merry-go-round, spinning around something we cannot see, moving at roughly 500,000 miles per hour through the spiral arms of the Milky Way. And the thing pulling us along, the anchor at the center of it all, weighs as much as 4 million suns compressed into a region smaller than the orbit of Mercury. Its name is Sagittarius A star. Astronomers call it SCR A star for short. And for decades, it was the galaxy's best-kept secret. The story of how we found it is not a story of a single observation or a single scientist. It is a story of arguments, false starts, stubborn data, and decades of staring at a part of the sky that refused to cooperate. Because the center of the Milky Way, the one place you would most want to see clearly if you were trying to understand how galaxies work, is buried behind so much dust and gas that visible light cannot punch through. Point an optical telescope toward the constellation Sagittarius, toward the densest part of the band of stars we call the Milky Way, and you hit a wall. The dust absorbs and scatters the light from anything sitting behind it. For most of human history, the galactic center was simply a blank. Radio waves, though, pass through dust like it is not even there. And in the early 1970s, radio astronomers started mapping the center of the galaxy with new instruments sensitive enough to pick up faint signals buried in the noise. What they found was a bright, compact radio source sitting almost exactly at the dynamical center of the galaxy, the point around which everything else seemed to be rotating. In 1974, two astronomers named Bruce Ballet and Robert Brown published a paper describing this source. They called it Sagittarius A star to distinguish it from other radio emissions in the region. At the time, nobody knew what it was. A dense cluster of stars, maybe. A region of hot ionized gas. Something strange, certainly, but strange in a way that still fit within the rules. The idea that it might be a black hole was not taken seriously at first. Black holes were still theoretical novelties in the 1970s. They had been predicted by Einstein's equations, sure, but most physicists treated them the way you treat a conversation about time travel. Fun to think about, probably not real. And even if black holes did exist, the idea that one could sit at the center of our galaxy, massive enough to influence the orbits of stars halfway across the disk, felt like science fiction. Galaxies were supposed to be held together by the collective gravity of their stars and dark matter, not by a single concentrated monster hiding in the middle. Then astronomers started watching the stars near Sagittarius A star, and those stars did not behave the way stars are supposed to behave. One star in particular, a bright blue giant designated S2, became the key. S2 orbits close enough to the galactic center that its full orbit takes only about 16 years. That is fast, absurdly fast, for something orbiting the center of a galaxy. Most stars in the Milky Way, including our Sun, take more than 200 million years to complete one lap. S2 does it in less than 2 decades. And not only is it fast, it is moving in an ellipse so stretched and so extreme that at its closest approach, it screams past Sagittarius A star at nearly 5% the speed of light. By the late 1990s and early 2000s, two independent teams, one led by Reinhard Genzel at the Max Planck Institute in Germany and the other led by Andrea Ghez at UCLA, had been tracking S2 and several other stars in the region for years. They used adaptive optics, a technique that compensates for the blurring caused by Earth's atmosphere, and infrared detectors that could see through the dust. And what they measured was unambiguous. The stars were not orbiting a cluster. They were not orbiting a cloud of gas. They were orbiting a single point, a point with no light, a point so small that even at those incredible speeds, the stars never collided with anything, and a point so massive that the only explanation consistent with the data was a supermassive black hole. The mass came out to about 4 million times the mass of the Sun. Not an estimate, not a guess, a measurement derived directly from the application of Kepler's laws to the observed orbits. You can argue about a lot of things in astrophysics. You cannot argue with orbital mechanics. If a star is moving in an ellipse, and you know the size of that ellipse and how long it takes to complete, you can calculate exactly how much mass is sitting at the focus. The math is ironclad. And the math said 4 million solar masses, concentrated in a region no larger than a few tens of millions of kilometers across. That is smaller than the distance from the Sun to Mercury. There is no known configuration of normal matter that can pack that much mass into that smaller space without collapsing into a black hole. No star cluster stays that compact. No cloud of gas resists its own gravity like that. The only object that fits is a black hole, and not just any black hole. A supermassive one. For their work, Genzel and Ghez were awarded the Nobel Prize in Physics in 2020. The Nobel Committee does not hand out prizes for maybes. They gave the prize because the evidence had become so overwhelming that the existence of Sagittarius A star as a supermassive black hole was no longer a hypothesis, it was a fact. But here is the strange part. Even after the mass was measured, even after the orbit of S2 had been tracked through multiple complete cycles, even after the Nobel Prize was awarded, no one had actually seen the black hole. Not in the sense that most people think of seeing something. There was no picture, no image of the object itself. What the astronomers had was a map of stellar motions. They had plotted the invisible anchor by watching the things it pulled. It was like deducing the existence of a planet by watching how a star wobbles, except scaled up to something 4 million times heavier than the sun. The direct image did not come until 2022. That was when the Event Horizon Telescope, a global network of radio dishes working together as a single Earth-sized instrument, released the first picture of Sagittarius A star's shadow. And shadow is the right word. What the image showed was not the black hole itself. You cannot photograph a black hole. What you can photograph is the light around it. The hot glowing gas spiraling inward, heated to millions of degrees by friction as it falls toward the event horizon. And at the center of that glow, a dark circle, the shadow cast by the black hole's gravity, the region where spacetime is bent so severely that light cannot escape. The image confirmed what the orbital measurements had already told us. There is a black hole at the center of the Milky Way. It weighs about 4.154 million times the mass of the Sun. It sits 26,996 light-years from Earth, give or take a few dozen light-years, depending on whose measurement you trust. And it has been sitting there, silent and invisible, for billions of years, quietly holding the galaxy together. 26,000 light-years is not a distance most people have any reference for. It is more than 200,000 trillion kilometers. Light, moving at 300,000 kilometers per second, takes 26 millennia to cross that gap. The light you would see tonight, if you could somehow look at Sagittarius A star directly, left its vicinity around the time humans were painting caves in southern France. The black hole you are trying to picture is not the black hole as it exists now. It is the black hole as it was when our ancestors were hunter-gatherers, long before agriculture, long before writing, long before anyone had the faintest concept that the glowing band across the night sky was a galaxy and that we were inside it. And yet, for all that distance, Sagittarius A star is close. Cosmically speaking, it is right next door. Most of the supermassive black holes we have studied in detail sit millions or even billions of light-years away, in the centers of distant galaxies we can barely resolve. Sagittarius A star is ours. It is the nearest supermassive black hole to Earth, and that proximity is the only reason we have been able to study it in the kind of detail that led to a Nobel Prize and a direct image. If the Milky Way were 10 times larger, or if we sat farther out in the galactic suburbs, we might still be guessing. The historical struggle to detect this thing is worth pausing on because it says something important about the limits of observation. For most of human history, the center of the galaxy was invisible, not because the technology did not exist. Before radio astronomy, the technology literally could not exist. Dust is opaque to visible light. No amount of patience or bigger mirrors would have helped. You needed a different kind of eye. And even after radio telescopes arrived, even after Ballet and Brown identified the bright radio source in 1974, the interpretation was murky. The mass estimate took another 2 decades to firm up. The image took nearly 50 years. What this means is that the most important object in our galaxy, the thing literally holding the whole structure together, was hidden from view for the entire span of recorded human civilization. The ancient Greeks did not know it was there. Newton did not know. Einstein, when he derived the equations that predict black holes, did not know there was one at the center of the Milky Way. The discovery is younger than most people reading this, and even now, with orbital data and a direct image and a Nobel Prize, there is still so much we do not understand. We know the mass, we know the location, we know the size of the event horizon. But we do not know how Sagittarius A star got that massive. We do not know when it formed. We do not know whether it grew smoothly over billions of years by swallowing gas and stars, or whether it assembled in violent bursts during galactic mergers. We do not know if it is currently growing, or if it has been starving for the last few million years. We do not even know for sure whether it is spinning, though most black holes probably are, and there are indirect hints that Sagittarius A star might be rotating at a significant fraction of the maximum speed allowed by physics. What we do know is that it is there. 4 million solar masses of spacetime curvature sitting at the gravitational center of everything we call home. The sun orbits it. The solar system orbits it. Every star you have ever seen in the night sky is orbiting it, and most of those stars will never get close enough to feel its pull directly. The galaxy is vast. The black hole, for all its mass, occupies an almost infinitesimally small fraction of the Milky Way's total volume. You could remove Sagittarius A star entirely, and most of the galaxy would barely notice. The stars would keep orbiting the collective gravitational field of all the other stars and dark matter. The spiral arms would persist, the disk would hold together, but near the center, in a region spanning just a few light years across, the black hole's influence is absolute. Stars in that zone are not orbiting the galaxy, they are orbiting Sagittarius A star. Their motions are dictated entirely by its gravity. They move in ellipses so extreme, so fast, and so precisely measured that astronomers can use them as test particles to probe the spacetime around the black hole. Every time S2 completes another orbit, it gives physicists another chance to check whether Einstein's equations still hold. So far, they do. Relativity predicts that the orbit should precess, that the ellipse should slowly rotate over time. And it does, exactly as predicted. The fact that we can test general relativity using a star orbiting a black hole 26,000 light-years away is one of the quiet miracles of modern astronomy. It is also a reminder of just how far observational technology has come in the last few decades. Adaptive optics, interferometry, infrared detectors sensitive enough to track individual stars through the glare of the galactic center. None of that existed 50 years ago. The discovery of Sagittarius A star as a supermassive black hole is not just a discovery about the galaxy. It is a case study in what becomes possible when instruments catch up to the questions, and the questions are piling up. Because Sagittarius A star is not just a curiosity, it is a template. Nearly every large galaxy we have looked at appears to have a supermassive black hole at its center. The Andromeda galaxy has one, the Sombrero galaxy has one. Even small galaxies, dwarf galaxies, seem to host black holes weighing millions of solar masses. The relationship between a galaxy's total mass and the mass of its central black hole is one of the tightest correlations in all of astrophysics, which suggests that the two are connected, that galaxies and their black holes grow together, somehow feeding off the same reservoirs of gas, shaping each other over billions of years. How that relationship works is still being argued over. Does the black hole form first and pull the galaxy together around it? Or does the galaxy form first and funnel gas inward to build the black hole? Do they grow in lockstep, or does one sprint ahead and drag the other along? We do not know. But Sagittarius A star, Because it is so close and so well measured, is where we go to look for answers. The invisible anchor is no longer invisible. We have weighed it. We have photographed its shadow. We have tracked the stars it controls. And what we have found is an object so dense, so extreme, that it bends space-time into a shape we are still learning to describe. Not just a void, not just an absence, a feature, a structure. A thing with properties, with history, with a future that will play out over timescales longer than the current age of the universe. And now, having found it, having finally dragged it into the light by measuring everything around it, we can start asking the next question. What does it mean for 400 billion stars to be tethered to a single point? What does it look like when an entire galaxy spins around an object the size of a solar system? What is actually happening in the space around that event horizon, where stars are screaming past at a measurable fraction of light speed and gas is glowing hot enough to emit X-rays? That is where this goes next, because Sagittarius A star is not just sitting there, it is conducting, it is pulling, it is shaping the motions of everything within its reach, and its reach extends farther than most people think. 400 billion stars. That is the latest estimate for how many stars live in the Milky Way, though the number keeps shifting depending on whose survey you trust and how you count the faint ones nobody can see directly. 400 billion. If you started counting right now, 1 star per second, 24 hours a day without stopping, it would take you more than 12,000 years to finish. And every single one of them, from the smallest red dwarf to the brightest supergiant, is moving in response to the same gravitational field. A field shaped, in large part, by a single invisible point at the center. That point is Sagittarius A star. And while it does not pull on every star in the galaxy equally, it sets the tempo, it anchors the core. It defines the geometry of the inner few light years, where the gravitational field becomes so steep that stars stop behaving like distant, leisurely wanderers and start behaving like test particles in a physics experiment. The kind of experiment where you can measure the curvature of space-time by watching something fall. From our vantage point, 26,000 light-years out, the Sun takes about 250 million years to complete one orbit around the galactic center. We call that span a galactic year. The last time Earth was in this same position relative to the galaxy, dinosaurs had not yet evolved. The orbit is slow, stately, almost boring in its predictability. The Sun is not close enough to the center to feel Sagittarius A star as anything more than one contributor among many to the overall gravitational field. Out here, the galaxy is a collective. No single object dominates, but closer in, the rules change. Within a few light-years of the galactic center, the black hole's gravity becomes the only thing that matters. Stars in that region are not orbiting the galaxy anymore. They are orbiting Sagittarius A star. And their orbits are not slow. They are violent, stretched, and fast enough that we can watch them move in real time, or close to it. Real time in this context means tracking a star over the course of a few years or a decade and seeing it shift position noticeably against the background. For most stars in the galaxy, that kind of motion is invisible without waiting millions of years. For the stars near Sagittarius A star, you can see it happen within a human career. Astronomers call them S-stars. The S stands for source, a leftover from the radio surveys that first catalogued the region. There are dozens of them mapped so far, all bright enough to be detected through the dust, all moving fast enough that their orbits can be measured with precision. Some take 30 years to complete an orbit, some take 100. And one, the star that became the key to everything, takes just 16. That star is called S2. It is a bright blue giant, roughly 15 times the mass of the Sun, young by stellar standards, probably only a few million years old, and it is screaming around Sagittarius A star in an ellipse so extreme that the difference between its closest and farthest approach is a factor of more than 10. At apocenter, the farthest point in its orbit, S2 is about 1,600 astronomical units from the black hole. An astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. So at its farthest, S2 is more than 1,000 times farther from the black hole than we are from the Sun. Still close, cosmically speaking, but far enough that the gravity feels almost gentle. Then the star swings back inward. At pericenter, its closest approach, S2 comes within about 1,400 Schwarzschild radii of the event horizon. The Schwarzschild radius is the size of the black hole's event horizon, the point of no return. For Sagittarius A star, that radius is roughly 12 million kilometers. So at its closest, S2 passes within about 17 billion kilometers of the black hole. That sounds like a lot. It is not. That is closer than the orbit of Neptune around our Sun. And at that distance, moving under the pull of 4 million solar masses concentrated into a region smaller than Mercury's orbit, S2 is moving fast. How fast? About 7,650 kilometers per second, roughly 17 million miles per hour, nearly 5% the speed of light. Fast enough that if you could somehow ride along with the star, relativistic effects would become noticeable. Time would pass slightly slower for you than for someone standing still far away. Light from distant stars would blue shift in front of you and red shift behind. The black hole's gravity would warp your view of the sky into a distorted funhouse version of the galaxy, where everything behind the event horizon simply disappears. No human technology has ever moved that fast. The fastest spacecraft we have ever built, the Parker Solar Probe, tops out at about 192 kilometers per second when it dives close to the Sun. S2 is moving 40 times faster. And it is not a tiny probe, it is a star. A massive, luminous ball of fusing hydrogen 15 times heavier than the Sun, whipping around a black hole in an ellipse that completes every 16 years like clockwork. The first person to notice S2 moving was an astronomer named Andreas Eckart, working with Reinhard Genzel's team in the mid-1990s. They were using the New Technology Telescope at the European Southern Observatory in Chile, equipped with an adaptive optics system that could correct for the blurring caused by Earth's atmosphere. Adaptive optics works by measuring how turbulence in the air distorts incoming light, then adjusting a deformable mirror hundreds of times per second to cancel out the distortion. The result is an image almost as sharp as if the telescope were sitting in space, almost. Good enough to pick out individual stars near the galactic center and track their positions over time. What Eckart and Genzel saw when they looked at infrared images of the region was a small cluster of bright stars near Sagittarius A star, all moving, not drifting slowly. Moving fast enough that if you compared images taken a year apart, the stars had visibly shifted. That alone was remarkable. Most stars in the sky stay in the same place relative to each other for centuries. These stars were moving fast enough that their motion was obvious within a single human observing season. Over the next few years, the team kept watching. They tracked S2 through multiple passages, refining its orbit with each new set of observations. By the early 2000s, the data were good enough to calculate the mass of whatever S2 was orbiting. The answer came back at about 4 million solar masses, concentrated in a region so small that the only explanation was a black hole, not a guess. A direct measurement derived from applying Kepler's laws to a star whose orbit had been tracked in painstaking detail. Andrea Gheze's team at UCLA was doing the same thing, independently, using the Keck Observatory in Hawaii. They tracked S2 and several other S-stars over the same period, using similar techniques and arriving at the same conclusion: 4 million solar masses, invisible, compact, a black hole. When both teams published their results, the case became airtight. The orbital mechanics do not lie. If a star is moving in an ellipse, and you know the size and period of that ellipse, the mass at the focus is a matter of basic arithmetic, and the arithmetic pointed to a supermassive black hole. But the story does not end there, because once you have an orbit measured that precisely, you can start testing more subtle effects. Effects predicted by general relativity that only show up in strong gravitational fields. Effects that would be invisible if the black hole were less massive or if the star's orbit were less extreme. S2's orbit is both massive and extreme, which makes it a natural laboratory for testing Einstein's equations in conditions we cannot replicate anywhere else. The effect in question is called orbital precession. In Newtonian physics, if you have two objects orbiting each other in isolation, the orbit is a perfect ellipse. It repeats exactly, tracing the same path through space over and over. But in general relativity, spacetime itself is curved by the presence of mass, and that curvature changes the shape of the orbit. The ellipse does not close. Instead, it slowly rotates, tracing out a rosette pattern over multiple orbits. The long axis of the ellipse, the line connecting the closest and farthest points, gradually shifts direction. This effect was first observed in the orbit of Mercury. Mercury is close enough to the Sun, and the Sun is massive enough that Mercury's orbit precesses by a tiny amount each century, 43 arcseconds per century to be exact. An arcsecond is 1/3600th of a degree. 43 arcseconds is almost nothing, a shift so small that it took more than a century of careful observations to detect. But it was real, and it was one of the first major confirmations of general relativity. Newton's laws predicted a smaller precession due to the gravitational pull of the other planets. General relativity predicted an additional shift caused by the curvature of spacetime near the Sun. The extra shift matched Einstein's prediction exactly. S2's orbit around Sagittarius A star should show the same effect, only much larger. The black hole is 4 million times more massive than the Sun. The gravitational field near the black hole is far stronger, and S2 gets much closer to the black hole, relatively speaking, than Mercury gets to the Sun. The predicted precession is not 43 arcseconds per century. It is about 12 arc-minutes per orbit. An arc-minute is 60 arcseconds, so we are talking about a shift roughly 16,000 times larger than Mercury's. And S2's orbit only takes 16 years, which means the precession should be visible within a human lifetime. You should be able to watch the orbit rotate in real time. Genzel's team set out to measure it. They used an instrument called Gravity, part of the Very Large Telescope Interferometer in Chile. Gravity is not a single telescope. It is 4 telescopes working together, combining their light to achieve the resolution of a telescope much larger than any one of them. The technique is called interferometry, and it is fiendishly difficult. You have to keep the light from all 4 telescopes perfectly synchronized, down to a fraction of a wavelength. But when it works, the resolution is extraordinary. Gravity can measure the position of a star near the galactic center to within a few tens of microarcseconds. A microarcsecond is 1/millionth of an arcsecond. It is the angular size of a golf ball on the Moon as seen from Earth. That level of precision is what makes it possible to detect orbital precession in S2. The results came in 2019, after tracking S2 through one full orbit, including its closest approach in 2018. The team reported that they had detected the precession. The orbit had shifted by about 12.1 arc-minutes, consistent with the predictions of general relativity. The significance was reported at 7 sigma when using just the gravity data, and 10 sigma when including older observations from an earlier instrument called NECO. In statistics, sigma measures how confident you are that a result is real and not just noise. 5 sigma is the standard threshold for claiming a discovery in physics. 10 sigma means the probability that the result is a fluke is less than 1 in several trillion. The precession is real. What makes this remarkable is not just that the orbit precesses, it is that the size of the precession matches general relativity's prediction so closely. If spacetime were not curved the way Einstein said it was, the orbit would look different. If there were extra mass near the black hole, maybe a cluster of dark objects or a swarm of smaller black holes, the orbit would look different. If gravity behaved differently at these scales, the orbit would look different, but it does not. It looks exactly the way Einstein's equations say it should, which means that within a few light years of a 4 million solar mass black hole, spacetime is doing what the theory predicts: curved, warped, bent into a shape that makes orbits rotate. S2 is not the only star whose orbit tells this story. There are dozens of other S-stars, all moving in similar ellipses, all under the same gravitational influence. Some are slower, some are faster. Some have been tracked for decades. Some were only discovered recently. Together, they paint a picture of a region of space where gravity is so strong that normal intuition breaks down. Stars do not move in straight lines. They do not move in simple circles. They move in stretched, precessing ellipses that twist and turn over time, carving out paths through spacetime that can only be explained by the presence of an enormous concentrated mass at the center. And here is the thing. These stars are not special. They are not exotic objects. They are just stars. Normal stars, made of the same hydrogen and helium as every other star in the galaxy. They are not doing anything unusual other than existing in a place where the gravity is extreme. The physics governing their motion is the same physics that governs the motion of the Moon around Earth or the planets around the Sun. The equations are the same. The principles are the same. The only difference is the scale. 4 million solar masses instead of 1. A pericenter distance measured in tens of astronomical units instead of hundreds of millions. And that difference in scale is enough to turn an ordinary orbit into a test of general relativity. The fact that we can measure this, that we can track a star over 16 years and detect a shift of 12 arc-minutes in its orbit, is a testament to how far observational astronomy has come. 50 years ago, this would have been impossible. The instruments did not exist. Adaptive optics did not exist. Interferometry at this level of precision did not exist. Even the idea of tracking individual stars near the galactic center was not seriously considered because nobody thought the resolution would ever be good enough. And now we are not just tracking them, we are using them to test fundamental physics. The numbers involved are worth sitting with for a moment. S2 weighs 15 times the mass of the Sun. Sagittarius A star weighs 4 million times the mass of the Sun. The ratio between them is more than 260,000 to 1. And yet, at closest approach, S2 comes within about 17 billion kilometers of the event horizon. The event horizon itself has a radius of about 12 million kilometers. So at pericenter, the star is only about 1,400 times farther from the event horizon than the event horizon is wide. That is close enough that tidal forces become significant. The side of the star facing the black hole feels slightly more gravity than the side facing away. Not enough to tear the star apart, but enough that if you could measure the star's shape precisely enough, you would see it stretched, elongated, pulled toward the black hole. We cannot measure that yet, but we can see the star's light. And in 2018, when S2 made its closest approach, astronomers detected a gravitational redshift in the star's spectrum. Light climbing out of a gravitational well loses energy, shifting toward longer, redder wavelengths. The deeper the well, the larger the shift. At the distance S2 reached during pericenter, the redshift was detectable. The light from the star was measurably redder than it should have been, by an amount that matched the predictions of general relativity. Another test, another confirmation, another piece of evidence that spacetime near Sagittarius A star behaves exactly the way the equations say it should. What does all this add up to? It means that Sagittarius A star is not just a black hole, it is a laboratory, a place where we can test the laws of physics in conditions that do not exist anywhere else within reach. A place where space-time is curved so dramatically that the effects are visible with instruments we can build today using stars that happen to be orbiting close enough for us to watch. And it means that the 400 billion stars in the Milky Way are not just a random collection. They are moving in a structure, a gravitational architecture with a clear center, a defined core, and a geometry that reflects the influence of the most massive single object in the galaxy. The dance metaphor is almost too perfect. Every star in the galaxy is moving under the influence of every other star, plus the dark matter, plus Sagittarius A star. The combined gravitational field is what holds the galaxy together. But in the innermost region, within a few light years of the center, the dance simplifies. The black hole dominates. The other stars matter less. And what you are left with is a clean, readable pattern, stars moving in ellipses, ellipses that precess. Precession that matches the predictions of a theory written down more than a century ago by a physicist who never imagined we would be able to test it at this scale. S2 will reach apocenter, the farthest point in its orbit, in 2026. After that, it will begin falling back toward the black hole, accelerating as it goes, picking up speed until it reaches pericenter again in 2034. Astronomers are already planning the observations. They will track the orbit again, more precisely this time, with better instruments and longer baselines. They will look for deviations from the expected path. They will search for hints of extra mass, hidden dark objects, anything that might perturb the orbit in ways general relativity does not predict. So far, there are no deviations. The orbit fits, the precession fits, the redshift fits. Everything fits. Which brings us to the next question. If spacetime near Sagittarius A star is curved enough to make orbits precess and light redshift, what is actually happening to the fabric of space itself? What does it mean for mass to warp spacetime? What does that curvature look like, feel like, behave like, if you could somehow get close enough to see it directly? The stars near the black hole are moving through something, not empty space, not a vacuum. Something with structure, with geometry, with properties that can be measured and tested. And that something is about to become the focus. Spacetime does not exist the way most people think it exists. It is not a stage, it is not a container, it is not a fixed backdrop against which events play out. Space by itself and time by itself are doomed to fade away into mere shadows, Einstein said. That is not poetry, that is physics. Space and time are aspects of a single unified thing, and that thing responds to the presence of mass and energy by curving. Not metaphorically, not sort of, actually curving in a way that can be measured, predicted and tested. This idea, the core of Einstein's general theory of relativity, was published in 1915. It replaced Isaac Newton's picture of gravity as a force that reaches across empty space and pulls objects toward each other. Newton's equations worked beautifully for most situations. They predicted planetary orbits. They explained tides. They sent spacecraft to the moon. But they could not explain everything. Mercury's orbit precessed slightly more than Newton's laws allowed. Light, which has no mass, should not be affected by gravity under Newton's framework, and yet starlight passing near the sun during a solar eclipse was observed to bend. And Newton himself was uncomfortable with the idea of action at a distance, the notion that gravity could reach across millions of miles of empty space instantaneously without any physical mechanism. Einstein solved all of that by getting rid of the force. In general relativity, gravity is not a force pulling you toward the Earth. Gravity is the shape of space-time around the Earth. The Earth's mass warps the geometry of space and time in its vicinity, and objects moving through that warped geometry follow curved paths. You are not being pulled toward the ground. You are moving along the straightest possible path through curved space-time, and that path happens to intersect the surface of the planet. The ground, in a very real sense, is accelerating upward into you. You feel weight because the surface of the Earth is pushing against you, preventing you from following your natural trajectory through space-time, which would be to fall. This is where the fabric analogy comes in, and it is both helpful and misleading. Picture a stretched rubber sheet. Place a heavy ball in the center. The sheet sags. The ball creates a depression, a well. Now roll a smaller ball across the sheet. It will not travel in a straight line. It will curve toward the depression, spiraling inward if it does not have enough speed to escape. That curvature is not because the small ball is being pulled by a force. It is because the sheet itself is curved, and the ball is following the shape of the surface. That is what mass does to space-time. Except space-time is not a two-dimensional sheet. It is four-dimensional, 3 dimensions of space plus 1 of time, all woven together into a structure that behaves more like a field than a fabric. And the curvature is not just spatial. Time itself is affected. Clocks run slower in stronger gravitational fields. Light takes longer to travel through regions of curved spacetime. The path of a photon bends not because the photon has mass, but because spacetime itself is bent, and the photon is following the straightest available path through that bent geometry. The mathematics of general relativity are notoriously difficult. The core equation, Einstein's field equation, relates the curvature of spacetime to the distribution of mass and energy within it. On one side of the equation, you have a term describing how spacetime curves. On the other side, you have a term describing how much mass and energy is present. The equation says, in essence, that matter tells spacetime how to curve, and curved spacetime tells matter how to move. That phrasing is often attributed to physicist John Wheeler, and it captures the elegance of the theory. Geometry and physics are the same thing. The shape of spacetime is gravity. Einstein spent years working out the details. The theory had to reduce to Newton's laws in weak gravitational fields where the curvature is small. It had to explain the precession of Mercury's orbit. It had to predict the bending of light. And it had to do all of this using a consistent mathematical framework that did not break down under extreme conditions. When Einstein finally published the full theory in 1915, it was immediately clear that he had done something extraordinary. Within a few years, observations during a solar eclipse confirmed that starlight was bent by the sun's gravity, exactly as the theory predicted. Einstein became a celebrity. General relativity became the foundation of modern cosmology. But the theory also predicted things that seemed absurd. Black holes, for instance. If you pack enough mass into a small enough region, the curvature of spacetime becomes so extreme that nothing, not even light, can escape. The equations allowed for this, but most physicists, including Einstein himself, were skeptical that such objects could actually exist in nature. They seemed like mathematical curiosities, solutions to the equations that did not correspond to anything real. We now know they are real. And Sagittarius A star is one of the most extreme examples we have ever studied. 4 million solar masses packed into a region smaller than the orbit of Mercury. The curvature of spacetime near that object is not a subtle effect. It is not a correction you apply to Newtonian physics to get slightly better predictions. It is the dominant feature of the local environment. Space and time near Sagittarius A star are bent so severely that the rules governing motion, light, and even the passage of time are fundamentally different than they are out here. Let us start with the simplest effect, light bending. When light passes near a massive object, its path curves. The closer the light gets to the object, the more it curves. This is called gravitational lensing, and it happens because the light is following a straight path through curved spacetime. From the perspective of the photon, it is traveling in a straight line. From our perspective, watching from far away, the path looks bent. Near Sagittarius A star, this effect is extreme. Light passing close to the event horizon bends so sharply that it can loop around the black hole multiple times before either escaping or falling in. If you were somehow hovering near the event horizon and looked outward, you would see multiple distorted images of the same distant stars, stacked on top of each other in a series of concentric rings. This is not science fiction. This is what general relativity predicts, and it is what we see in simulations of light paths near black holes. The famous image of Sagittarius A star, released by the Event Horizon Telescope in 2022, shows exactly this kind of lensing. The bright ring of light around the black hole is not the event horizon itself. It is light from hot gas orbiting the black hole, bent and focused by the curvature of spacetime into a ring shape. The dark circle in the center, the shadow, is the region where spacetime is so curved that light cannot escape. That shadow is smaller than you might expect. For a black hole with 4 million times the mass of the Sun, the event horizon has a radius of about 12 million kilometers. That sounds large until you remember that the Sun itself has a radius of about 700,000 kilometers. So the event horizon of Sagittarius A star is only about 17 times wider than the Sun, despite being 4 million times heavier. And from Earth, 26,000 light-years away, that translates to an angular size of about 50 microarcseconds. A microarcsecond is 1/1,000,000th of an arcsecond, which is 1/3600th of a degree. 50 microarcseconds is the angular size of a donut on the Moon, as seen from Earth. Detecting something that small required linking radio telescopes across the entire planet to create an Earth-sized virtual telescope. The fact that we succeeded is a minor miracle of engineering. But the image is only part of the story. What matters for understanding space-time curvature is not just what we see, but what the curvature does to the things moving through it. And near Sagittarius A star, the effects are dramatic. Consider the star S2 again, the one we talked about in the last section. At its closest approach, S2 comes within about 17 billion kilometers of the event horizon. That is roughly 1,400 times the radius of the event horizon. In terms of the black hole's gravitational influence, that is close. Close enough that the gravitational field is no longer uniform. The side of the star facing the black hole feels more gravity than the side facing away. This difference in gravitational pull is called a tidal force, and it is a direct consequence of space-time curvature. Tidal forces are not unique to black holes. You experience them on Earth. The moon's gravity pulls on the oceans, creating tides. The side of Earth facing the moon feels slightly more pull than the side facing away. The difference is small because the moon is not very massive and Earth is relatively large. Near a black hole, the effect is much stronger. If you were falling feet first into Sagittarius A star, the tidal forces would eventually stretch you vertically and compress you horizontally, a process astrophysicists cheerfully refer to as spaghettification. For S2, the tidal forces are not strong enough to tear the star apart, but they are strong enough that if we could measure the star's shape precisely enough, we would see it elongated, stretched toward the black hole. Time is affected too. Clocks run slower in stronger gravitational fields. This is called gravitational time dilation, and it is one of the most counterintuitive predictions of general relativity. If you were standing on the surface of a planet, your watch would tick slightly slower than an identical watch held by someone in orbit above you. The effect is tiny for everyday situations, but it is real and measurable. GPS satellites have to account for time dilation because their clocks run slightly faster in the weaker gravitational field of orbit than clocks on the ground. If the corrections were not applied, GPS navigation would drift by several kilometers per day. Near Sagittarius A star, time dilation is not a tiny correction. It is a major effect. If you are hovering just outside the event horizon, watching a clock held by someone far away from the black hole, you would see their clock ticking faster than your own. Not slightly faster, much faster. Seconds for you would be minutes or hours for them. And if you crossed the event horizon, time from the perspective of the outside universe would effectively stop. Photons emitted by you as you fell would be redshifted to longer and longer wavelengths, dimming and fading until you disappeared from view. From your perspective, nothing unusual would happen. You would fall through the event horizon in a finite amount of your own time, but from the perspective of someone watching from far away, you would appear to slow down, freeze and fade, never quite reaching the horizon. You would be stuck there forever in their reference frame, a ghost image frozen at the edge. This is not a trick of perception, it is a real feature of curved spacetime. Time itself runs at different rates, depending on where you are and how strong the gravitational field is. And near a black hole as massive as Sagittarius A star, the difference is profound. Now let us talk about the liquid glass metaphor. It is not a term you will find in textbooks, but it captures something important about how spacetime behaves near a black hole. Spacetime is not rigid, it is not fixed. It responds to the presence of mass and energy by deforming, and the deformation is smooth and continuous. If you could somehow visualize spacetime as a physical medium, it would look less like a solid grid and more like a viscous fluid, bending and flowing around concentrations of mass. Near Sagittarius A star, the curvature is so extreme that spacetime behaves less like empty space and more like a lens. Light paths twist, trajectories bend, objects moving through that region are constantly falling, accelerating, curving inward, following the shape of the geometry they are embedded in. The liquid glass analogy works because it conveys the way spacetime can focus and distort light, much like a piece of glass with a complex shape, bends light passing through it. Gravitational lensing near a black hole creates multiple images, magnifications, and distortions that are strikingly similar to what you see when you look through a curved piece of glass or a drop of water. The light itself is not being absorbed or scattered. It is following curved paths through a medium whose geometry has been warped by the presence of enormous mass. And just as a carefully shaped lens can focus light to a point, the spacetime around a black hole can focus light into rings, arcs, and multiple overlapping images of the same object. The Event Horizon Telescope image of Sagittarius A star is a direct visualization of this effect. The bright ring is not a physical structure. It is light from gas orbiting the black hole, bent and amplified by the curvature of spacetime. Some of that light comes from gas on the far side of the black hole, behind the event horizon from our point of view. But spacetime is so curved that the light bends around the black hole and reaches us anyway, creating a glowing halo that completely surrounds the shadow. The photons are not taking shortcuts. They are following the only paths available to them through the bent geometry of spacetime. And those paths happen to curve around the black hole in a way that makes the light visible from all directions at once. The size of the shadow is determined by the mass of the black hole and the equations of general relativity. For Sagittarius A star, the predicted shadow diameter is about 52 microarcseconds. The observed shadow diameter is about 52 microarcseconds. The agreement is not approximate, it is exact to within the measurement uncertainties. That is a direct confirmation that spacetime near Sagittarius A star is curved in the way general relativity predicts. If the theory were wrong, if spacetime behaved differently under extreme conditions, the shadow would be a different size. It is not. The theory works. And this is where the real power of general relativity becomes clear. It is not just a description of gravity, it is a description of the geometry of the universe. Every prediction the theory makes about how spacetime should curve, how light should bend, how time should dilate, is testable. And so far, every test has confirmed the theory. Mercury's orbit precesses by the predicted amount. Starlight bends by the predicted amount near the Sun. Gravitational waves, ripples in spacetime, caused by accelerating masses, were detected in 2015, a century after Einstein predicted their existence. The orbits of stars near Sagittarius A star precess by the predicted amount. The shadow of Sagittarius A star has the predicted size. The redshift of light climbing out of the gravitational well matches the predictions. Over and over, in situation after situation, the theory holds. But there is a limit to how far we can push it. General relativity is a classical theory. It does not account for quantum mechanics, the other great pillar of modern physics. At scales smaller than the event horizon, inside the black hole, where all the mass is compressed into a point called the Singularity, general relativity predicts that spacetime curvature becomes infinite. Infinite curvature is another way of saying the theory breaks down. It stops making predictions. It hits a wall. Physicists call this a singularity, and it is a sign that something is missing from the picture. A complete theory of gravity would need to incorporate quantum mechanics, and no one has figured out how to do that yet. For now, though, outside the event horizon, general relativity works perfectly. And what it tells us is that spacetime is not a passive stage. It is an active participant in the physics. It bends, it curves, it responds to mass and energy. And near an object like Sagittarius A star, spacetime is bent so dramatically that the geometry dominates everything. Light cannot travel in straight lines, time cannot pass at a uniform rate, orbits cannot remain fixed. Everything is shaped by the curvature, molded by it, defined by it. The 4 million solar masses of Sagittarius A star do not just create a gravitational pull. They create a region of space where the rules are different, where motion is constrained by geometry, where light bends into rings and shadows, where time itself slows to a crawl as you approach the edge. That edge, the boundary between the region where escape is still possible and the region where it is not, is called the event horizon, and it is the most extreme feature of curved spacetime we know of. Cross it, and you are no longer in the same universe as the rest of us. You are in a region of spacetime that is causally disconnected from the outside. Nothing that happens inside can ever send a signal out. No light, no particles, no information of any kind. General relativity predicted this boundary. It predicted its size, its shape, its properties, and now, more than a century later, we have photographed it. We have seen the shadow it casts, we have measured its diameter to within a fraction of a percent, and we have confirmed, beyond any reasonable doubt, that spacetime near Sagittarius A star behaves exactly the way the equations say it should. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. That is not a metaphor. That is the law. What happens at the edge, though, at the event horizon itself, is something different. That boundary is where spacetime curvature reaches a critical threshold. It is where the geometry becomes so extreme that not even light can climb back out. And understanding what that means, what it looks like, what it does to anything that crosses it, requires us to look even closer, to step up to the edge of the abyss and peer in. There is a place around Sagittarius A star where the rules change absolutely, not gradually, not as a matter of degree, absolutely. On one side of this boundary, escape is difficult but possible. Throw something outward fast enough, and it will climb away from the black hole, fighting gravity all the way, but eventually making it out. On the other side, escape is not difficult, it is impossible. Throw something outward, at any speed, at light speed, at 1,000,000 times light speed if physics allowed it, and it will still fall inward forever. There is no way out, no trick, no loophole, no clever trajectory that lets you slip free. Cross that line, and you are done. This boundary is called the event horizon, and it is the most unforgiving edge in the universe. The name is precise. An event is anything that happens, a photon emitted, a particle decaying, a clock ticking, anything. And a horizon is a boundary beyond which you cannot see. Stand on a flat plane and look toward the distance. There is a point where the curvature of the Earth hides everything beyond. That is your horizon. The event horizon of a black hole works the same way, except instead of the Earth's surface curving away from you, it is space-time itself that curves so steeply that events occurring beyond the boundary can never send signals back. Not because the signals are too faint, not because they are blocked, because the geometry of spacetime will not allow it. Light emitted inside the event horizon cannot travel outward. It can only travel inward or sideways, briefly, before spacetime curves it back toward the center. The paths through spacetime that lead outward simply do not exist inside that boundary. For Sagittarius A star, the event horizon sits at a radius of about 12 million kilometers from the center. 12 million kilometers is not a small distance. It is roughly 80 times the radius of the Sun. You could fit about 17 suns side by side across the diameter of Sagittarius A star's event horizon. But that is the horizon around 4 million solar masses, 4 million suns, crushed into a region where 17 normal suns would fit. The ratio is absurd. And the horizon itself is not a thing. It is not a shell. It is not a membrane. It is not a surface you could touch or bounce off of. It is a mathematical boundary in space-time, a line in the sand drawn by geometry. The size of the horizon is determined by the mass of the black hole. The relationship is direct and simple. Double the mass, double the radius. Triple the mass, triple the radius. The formula is called the Schwarzschild radius, named after Karl Schwarzschild, the German physicist who derived the first exact solution to Einstein's field equations in 1915, just months after the theory was published. Schwarzschild was serving in the German army during World War I when he did this work, calculating the geometry of space-time around a spherical mass while stationed on the Russian front. He sent his results to Einstein in December of 1915. Einstein was stunned. He had not expected anyone to find an exact solution so quickly. Schwarzschild died a few months later from an illness contracted during the war. He was 42. His solution outlived him by more than a century and became the foundation for understanding black holes. The Schwarzschild radius depends on only one number, the mass. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. That means if you could somehow crush the Sun down to a sphere 3 kilometers wide, it would become a black hole. The event horizon would form at that radius, and light would no longer be able to escape. For an object with 4 million times the mass of the Sun, the Schwarzschild radius is about 12 million kilometers. For a black hole with the mass of Earth, the radius would be about 9 millimeters. Crush Earth down to the size of a marble and it becomes a black hole. The mass does not change. The gravity at a given distance does not change. What changes is that all the mass is now concentrated in such a small region that there exists a radius where the escape velocity equals the speed of light. Inside that radius, escape is impossible. Escape velocity is the speed you need to throw something upward for it to escape a gravitational field entirely. On Earth, escape velocity is about 11 kilometers per second. Launch a rocket at that speed and it will coast away from Earth forever, never falling back. Launch it slower and it will arc back down. The escape velocity depends on how massive the object is and how far you are from its center. Get closer to Earth's center and the escape velocity increases because you are deeper in the gravitational well. But Earth has a surface. You cannot get closer to the center than about 6,400 kilometers, the radius of the planet. So the maximum escape velocity you experience on Earth is 11 kilometers per second, calculated at the surface. A black hole has no surface, or more accurately, the event horizon is the effective surface, but it is not made of matter. It is just the radius where escape velocity equals the speed of light. For Sagittarius A star, that radius is 12 million kilometers. Sit at that distance and throw a rock outward. To make it escape, you would need to throw it at the speed of light. Sit a little farther out, say 15 million kilometers, and the required speed drops below light speed. Escape is possible. Sit a little closer, say 10 million kilometers, and the required speed exceeds light speed. Escape is impossible. The event horizon is the boundary where the required speed crosses the light speed threshold. Why does that matter? Because nothing can move faster than light. This is not a technological limitation. It is not that we have not built fast enough rockets. It is that the structure of space-time itself forbids it. Light speed is the maximum speed at which information, energy or matter can travel through space, period. There are no exceptions in the known laws of physics. So if you are inside the event horizon, where the escape velocity exceeds light speed, you cannot escape, not because you lack a powerful enough engine, because the universe does not allow it. This is where the black hole gets its name. Light cannot escape from inside the event horizon. Shine a flashlight outward from just inside the boundary, and the light does not climb away, it falls inward. From the perspective of someone far away, watching, the black hole emits no light from within that radius. It is black, perfectly black, not because it absorbs light, though it does that too, but because the geometry of space-time inside the horizon is such that all paths, including the paths that light travels, lead inward. There is no outward direction, not in any meaningful sense. This is hard to visualize because in our everyday experience, outward is always an option. Stand anywhere on Earth and you can point away from the ground. That direction is outward. Inside a black hole's event horizon, space-time is curved so severely that the equivalent of pointing away from the ground does not correspond to a direction that takes you farther from the center. All directions, from the perspective of someone inside, lead closer to the singularity at the center. The future, the forward direction in time, points inward. Trying to move outward is like trying to move backward in time. It is not just difficult. It is not something the structure of space-time allows. From the outside, an observer watching something fall toward the event horizon sees something strange. As the object approaches the boundary, time dilation kicks in. Clocks on the falling object tick slower and slower relative to the observer's clock. Light from the object is redshifted, stretched to longer wavelengths, dimmed. The object appears to slow down, moving slower and slower as it gets closer to the horizon. It never quite seems to reach it. The light coming from the object gets redder and fainter, stretched to infrared, then radio waves, then wavelengths so long that no detector could pick them up. The object fades from view, frozen at the edge. From the perspective of the outside observer, the object takes infinite time to cross the event horizon. From the perspective of the falling object, nothing strange happens at the horizon itself. Time passes normally. The object crosses the boundary in a finite amount of its own time. There is no wall, no barrier, no sensation of crossing. The horizon is not a place where anything physically changes. It is a coordinate boundary, a line in space-time that marks a point of no return. Once across, the object continues falling inward, accelerating toward the singularity at the center. But no signal from the object after it crosses can ever reach the outside. The events happening inside the horizon are causally disconnected from the universe outside. They might as well be happening in a different universe. This is the sense in which the event horizon is a horizon. Events inside it are hidden, not temporarily, not because they are far away, permanently hidden by the structure of space-time itself. If you drop a clock into a black hole and it crosses the event horizon, you will never receive another signal from that clock. Not if you wait 1 billion years, not if you build a telescope the size of the solar system. The clock is gone. The information about what happens to it after it crosses is gone. From the perspective of the outside universe, the clock has been erased. Does the clock still exist? That is a question physicists argue about. From the clock's own perspective, yes, it continues to exist, continues to tick, continues to fall, but its existence is no longer part of the causal future of anything outside the horizon. It cannot affect the outside universe in any way. It cannot send signals, it cannot exert forces. It is, for all practical purposes, gone. Some physicists take this further and argue that the information carried by the clock, the exact state of every atom in it, is lost when it crosses the horizon. That claim leads to the black hole information paradox, one of the deepest unsolved problems in theoretical physics. General relativity says the information is lost. Quantum mechanics says information cannot be destroyed. both theories cannot be fully correct. Something has to give. We do not know what. For now, set the paradox aside. Focus on the boundary itself. The event horizon of Sagittarius A star sits at a radius of 12 million kilometers. For a non-rotating black hole, the horizon is a perfect sphere. Schwarzschild's solution assumes the black hole is not spinning. Real black holes almost certainly spin, and spin changes the shape and size of the horizon. A spinning black hole has a smaller event horizon and an additional boundary outside it, called the ergosphere, a region where spacetime itself is dragged around the black hole. Sagittarius A star probably spins. We do not know how fast. Estimates suggest it could be spinning at a significant fraction of the maximum rate allowed by general relativity. If true, the event horizon would be slightly smaller than 12 million kilometers, and the geometry near the horizon would be more complicated. But for simplicity, and because we do not have precise measurements of the spin yet, most discussions treat Sagittarius A star as a Schwarzschild black hole. The basic picture holds: a spherical boundary, a point of no return, a radius where escape velocity equals light speed. 12 million kilometers sounds large until you remember what it is around. 4 million suns, that much mass packed into a sphere 80 times the size of a single sun. The density at the event horizon is not meaningful because the event horizon is not a material surface. The mass is all concentrated at the singularity in the center. The event horizon is just the boundary around that singularity, the radius where light cannot escape. But the average density inside the event horizon, if you calculated it, is not as extreme as you might think. Mass divided by volume. 4 million solar masses divided by the volume of a sphere with a 12 million kilometer radius. The result is about 1,000 kilograms per cubic meter. That is roughly the density of water. The average density inside Sagittarius A star's event horizon is less than the density of rock, less than the density of Earth, about the same as the density of a human body. This is not a trick, it is a consequence of how black holes scale. The Schwarzschild radius grows linearly with mass. The volume grows as the cube of the radius. So the average density inside the event horizon drops as the black hole gets more massive. For a black hole with the mass of the Sun, the average density is enormous, many times the density of an atomic nucleus. For a supermassive black hole like Sagittarius A star, the average density is low. If you were falling towards Sagittarius A star and crossed the event horizon, you would not be crushed instantly. The tidal forces at the horizon are relatively gentle for a black hole this massive. You would cross the boundary, still intact, and continue falling. The crushing comes later, closer to the center, where the tidal forces grow strong enough to rip atoms apart. At the horizon itself, you could survive, briefly. The tidal forces depend on the gradient of the gravitational field, how quickly gravity changes as you move from one point to another. Near a small black hole, the gradient is steep. Your feet, closer to the center, feel much more pull than your head. The difference is enough to tear you apart before you reach the horizon. Near a supermassive black hole, the gradient is gentler. The gravitational field is strong, but it does not change as rapidly over short distances. An astronaut falling into Sagittarius A star would cross the event horizon more or less intact. The spaghettification, the stretching and crushing, would happen deeper inside, closer to the singularity, where the tidal forces become extreme. But here is the problem. Once you cross the horizon, there is no coming back. You cannot change your mind, you cannot fire your rockets and pull up. The event horizon is not a place where you can hover. You cannot sit at the boundary and decide whether to cross. If you are close enough to see the horizon, you are already falling toward it. The only way to avoid crossing is to stay far away, outside the radius where your orbit decays. And once you cross, your future is fixed. You will hit the singularity. General relativity says so. The equations are deterministic. Once you are inside, every possible trajectory through spacetime leads to the center. There is no trajectory that leads back out. It is not that you are being pulled harder. It is that the geometry of spacetime inside the horizon is such that the singularity is in your future the same way tomorrow is in your future. You cannot avoid tomorrow by moving in space. You cannot avoid the singularity by moving in space. Inside the horizon, the singularity is not a place. It is a time, a moment you are moving toward, unavoidably, the same way you move toward the next second. The fate of light inside the event horizon is the same. A photon emitted just inside the boundary, aimed outward, does not travel outward. Space-time is curved so steeply that the outward direction, as defined by the photon's trajectory, curves back toward the center. The photon's path through space-time spirals inward, falling toward the singularity. Light emitted tangentially, sideways, might orbit the black hole briefly before falling in, but no trajectory leads out. The event horizon is the boundary where the future light cone, the set of all possible paths light can take into the future, tilts so far inward that it no longer includes any outward directions. This is why the black hole looks black. Photons cannot escape from inside. They cannot carry information out. They cannot reach your eye or your telescope. The only light you see comes from outside the horizon. The glowing gas orbiting the black hole, the stars whipping past nearby, the background glow of the galaxy. But the region inside the horizon emits nothing. It is a hole in the visible universe, a place where light goes to die. From the perspective of the outside universe, the event horizon is the ultimate prison. Whatever crosses it is lost, not hidden behind a wall. Not locked in a vault you could break into with enough effort. Lost in a way that is enforced by the structure of space-time itself. The horizon is a one-way membrane in time. Future points inward, past points outward. You can move from past to future, outside to inside, but not the other way. The asymmetry is absolute, and yet the horizon is not a special place for someone falling across it. This is one of the most counterintuitive aspects of general relativity. If you were falling into Sagittarius A star, instruments in hand, recording data, taking measurements, you would not detect anything unusual as you crossed the event horizon. Your clock would tick normally. Your instruments would function. The temperature would not spike. There would be no flash of light, no wall of fire, no dramatic boundary marker. You would cross the horizon the same way you cross the equator on Earth. It is a line on a map, a coordinate, not a physical feature you can feel. Only later, after you have crossed, would you realize something has changed. The stars behind you would appear to move strangely. Light from the outside universe would be compressed into a shrinking circle, blue shifted and brightened as space-time curvature focuses it. Ahead of you, toward the singularity, space-time would stretch and darken, and you would realize, too late, that every direction you try to move takes you closer to the center. The time dilation near the horizon is worth pausing on, because it is central to how black holes interact with the outside universe. Clocks run slower in stronger gravitational fields. This is called gravitational time dilation, and it is a prediction of general relativity that has been tested and confirmed repeatedly. GPS satellites experience it. Atomic clocks at different altitudes tick at different rates. The effect is small in everyday situations, but near an event horizon, the effect is extreme. Imagine you are hovering far from Sagittarius A star, watching a colleague fall toward the event horizon. Your colleague is sending you signals once per second by their clock, light signals, beeps, whatever. At first, you receive the signals at roughly 1 per second. As your colleague falls closer to the horizon, the signals start to arrive more slowly. The time between beeps stretches. 1 per second becomes 1 every 2 seconds, then 1 every 10 seconds, then 1 every minute. The signals are also redshifted. The light carrying them is stretched to longer wavelengths, dimmer and redder. Your colleague is not moving slower from their own perspective. Their clock is ticking normally. But from your perspective, far away, their clock is running slower. Seconds for them are minutes for you, then hours, then days. As they approach the horizon, the time dilation becomes infinite. The final signal sent just as they cross takes forever to reach you. It never quite arrives, or it arrives so redshifted, so stretched, that it becomes undetectable. Your colleague appears to freeze at the horizon, fading from view, never quite crossing. But from your colleague's perspective, nothing strange happens. They cross the horizon in a finite amount of their own time. The signals they send after crossing simply never reach you. Not because they are blocked, because space-time will not allow them to propagate outward. The geometry forbids it. So from the outside, your colleague appears to freeze and fade at the horizon. From the inside, they cross and continue falling. Both perspectives are correct. They are describing the same event from different frames of reference. And the resolution is that the event horizon is a boundary in space-time where time, as measured by an outside observer, effectively stops. This is why black holes are sometimes described as frozen stars. When a massive star collapses to form a black hole, the collapse does not look instantaneous from the outside. The surface of the star appears to slow down as it approaches the Schwarzschild radius, redshifting and dimming, freezing at the boundary. From the perspective of someone on the surface, the collapse continues normally. The star crosses its own Schwarzschild radius and becomes a black hole in a finite amount of time. But from the outside, the star appears to hover at the edge forever, frozen in time. The term frozen star was used in the early decades after Schwarzschild's solution was published. The term black hole did not catch on until the 1960s, when John Wheeler popularized it. Wheeler himself did not coin the phrase. It emerged during a conference in 1967, and Wheeler adopted it. The name stuck because it is vivid. It captures the essential feature, a region of space that is black because light cannot escape. The event horizon of Sagittarius A star is not something you can see directly. It does not glow. It does not emit radiation. What you see is the shadow it casts. The Event Horizon Telescope image from 2022 shows a dark circle surrounded by a bright ring. The dark circle is the shadow. It is slightly larger than the event horizon itself because light passing near the horizon is bent so strongly that it curves around the black hole. The shadow includes not just the event horizon, but also a region just outside it, called the photon sphere, where light can orbit the black hole in unstable circular paths. The radius of the shadow is about 2.6 times the Schwarzschild radius. For Sagittarius A star, that translates to about 31 million kilometers, still tiny from 26,000 light-years away. Still small enough that it took an Earth-sized telescope to resolve it, but visible, photographable, real. That shadow is the closest we can get to seeing the event horizon. It is the silhouette of a boundary we can never cross and return from, a place where the rules change absolutely, where escape becomes impossible, where time, as measured from the outside, stops, where light falls inward and never comes back. The edge of the black hole is not a place. It is a threshold in spacetime, a line that divides the universe into two regions, one where the future is open and uncertain, one where the future leads inevitably to the singularity at the center. And everything that crosses that line, every atom, every photon, every bit of information is drawn inward towards something we cannot see, cannot measure, and can barely describe with the equations we have, the singularity. The point where space-time curvature becomes infinite and the laws of physics, as we understand them, break down completely. That is where we are headed next. Not because it is a place anyone can visit and return from, but because understanding what happens at the center of a black hole is the only way to understand what a black hole really is. The event horizon is the door. The singularity is what lies beyond. You have crossed the event horizon. Your clocks are still ticking. Your instruments are still recording data. From your own perspective, nothing dramatic has happened. You did not hit a wall. You did not feel a jolt. You did not notice the moment you passed through the boundary. But something fundamental has changed. The universe you knew, the one where escape was still an option if you fired your engines hard enough, no longer exists in your future. Every trajectory through space-time now leads in one direction, inward, toward the center, toward the singularity. The singularity is not a place you can visit and report back from. It is not a small, dense object sitting at the center of the black hole that you could photograph or measure and then leave. It is the end of your timeline, the final moment, the last tick of your clock. In the geometry of a black hole, the singularity is not a location in space. It is a moment in time, a point in your future that you are moving toward the same way you move toward next Tuesday. And just as you cannot avoid next Tuesday by walking in a different direction, you cannot avoid the singularity by changing your trajectory through space. Once inside the event horizon, reaching the singularity is as inevitable as reaching the next second. How long does it take to get there? That depends on the size of the black hole and where you cross the event horizon. For Sagittarius A star, with an event horizon radius of about 12 million kilometers, an object falling straight in from the horizon would reach the singularity in about 17 seconds of its own time. 17 seconds, not 17 years, not 17 hours. 17 seconds from the moment you cross the point of no return to the moment space-time curvature becomes infinite and the equations stop working. If you fell in feet first, you would have roughly 17 seconds to contemplate what was about to happen before it happened. Not long enough to write a memoir, barely long enough to regret your choices. And during those 17 seconds, the tidal forces would become noticeable, then extreme, then lethal, then beyond anything the word lethal can describe. The singularity at the center of a black hole is not just a point of infinite density. It is a place where the curvature of space-time itself becomes infinite. And as you fall toward it, the gradient of the gravitational field, the rate at which gravity changes from one point to another, grows steeper and steeper. Your feet, closer to the singularity than your head, feel more pull. The difference starts small. Then it grows, then it dominates everything. Physicists call this effect spaghettification. The term is informal but accurate. You are stretched lengthwise, like a piece of dough being pulled into a long, thin strand. At the same time, you are compressed sideways, squeezed horizontally while being stretched vertically. The forces do not come from the singularity reaching out and grabbing you. They come from the geometry of space-time itself. Space-time near the singularity is curved so steeply that objects moving through it experience tidal forces strong enough to overcome every other force holding matter together. chemical bonds, electromagnetic forces, the strong nuclear force holding atomic nuclei together. All of it gets overpowered. The process is not instantaneous, it is progressive. At first, the tidal forces are gentle. You might feel a slight stretching sensation, like someone is pulling on your feet while holding your head still. Then the stretching intensifies, your body elongates, your bones creak, your muscles tear, then your cells rupture. Then the molecules inside those cells are pulled apart, then the atoms, then the subatomic particles. By the time you are within a few meters of the singularity, assuming you could somehow remain coherent that long, you would be a stream of elementary particles stretched into a thin line, falling inward at close to the speed of light. The tidal forces depend on the mass of the black hole. Larger black holes have gentler tidal forces at the event horizon because the curvature gradient is less steep. Sagittarius A star is massive enough that you could cross the event horizon more or less intact. A stellar mass black hole with only a few times the mass of the Sun would rip you apart before you reached the horizon. The tidal forces scale inversely with the square of the black hole's mass. Double the mass and the tidal forces at the horizon drop by a factor of 4. Sagittarius A star, at 4 million solar masses, has tidal forces at the horizon that are trillions of times weaker than those around a stellar mass black hole. Still strong enough to kill you eventually, just not immediately. But closer to the singularity, the tidal forces become extreme regardless of the black hole's size. The singularity is a point where the curvature of spacetime diverges, goes to infinity. The tidal forces near it grow without bound. There is no material, no structure, no configuration of matter that can withstand them. Everything gets stretched, everything gets crushed, everything gets torn apart at the most fundamental level physics allows. And then, at the singularity itself, the equations of general relativity produce infinities, infinite curvature, infinite density, infinite tidal forces, numbers that make no physical sense. This is where general relativity breaks down. Not because the theory is wrong. It has been tested over and over, and it works beautifully everywhere we can test it. But a singularity is a place where the theory stops making predictions. It hits a wall. The equations produce infinities, and infinities are not physical quantities you can measure. They are a signal that something is missing from the picture, that the theory is incomplete, that new physics is needed to describe what actually happens at the center of a black hole. Most physicists believe that quantum mechanics, the other pillar of modern physics, must play a role at the singularity. General relativity is a classical theory. It treats spacetime as a smooth, continuous fabric that can be curved and bent but never torn or quantized. Quantum mechanics, on the other hand, tells us that everything at small enough scales is discrete, quantized. Space itself, time itself, might not be smooth at the smallest scales. There might be a minimum length, a minimum time, below which the classical picture breaks down. If that is true, then the singularity might not be a point of infinite curvature. It might be a region where spacetime itself becomes grainy, quantum, described by a theory we do not yet have. This theory is often called quantum gravity. It would merge general relativity and quantum mechanics into a single framework capable of describing what happens when gravity becomes strong enough that quantum effects dominate. We do not have such a theory yet. String theory is one candidate. Loop quantum gravity is another. There are others, but none of them have been tested experimentally because the regimes where quantum gravity matters, inside black holes and in the first fraction of a second after the Big Bang, are not accessible to experiment. We cannot build a particle collider powerful enough to probe the energy scales where quantum gravity kicks in, And we cannot send a probe into a black hole and get data back. So we are stuck with theory, mathematics, and educated guesses. Some of those guesses suggest that singularities might not exist at all. That when you account for quantum effects, the infinite curvature predicted by general relativity gets smoothed out, replaced by something finite, something extreme, yes, but not infinite. There are models where the singularity is replaced by a quantum bounce, a region where spacetime reaches a maximum curvature and then rebounds. There are models where the singularity is replaced by a fuzzy quantum region where space and time lose their usual meanings. There are models where the singularity is not a point, but a surface, a two-dimensional or even three-dimensional structure embedded in spacetime. A recent paper from 2026, reported in several physics summaries, proposed that the Schwarzschild singularity, the kind of singularity you find in a non-rotating black hole, might actually be a three-dimensional surface rather than a point. The idea challenges the textbook picture. Instead of all the mass being concentrated at a single point of infinite density, the mass might be distributed over a finite region with extreme but not infinite curvature. The paper is speculative. It has not been confirmed. But it is part of a broader trend in theoretical physics toward questioning whether singularities are real or whether they are artifacts of using a classical theory in a regime where it should not apply. The point is that nobody knows what actually happens at the center of a black hole. General relativity says there is a singularity. Quantum mechanics suggests there might not be. And until we have a working theory of quantum gravity, tested and confirmed, the question remains open. What we do know is that whatever is there, it is hidden behind the event horizon. No signal from the singularity can reach the outside universe. No information about what happens there can escape. The event horizon acts as a one-way information barrier, and that barrier is absolute. So why does it matter if we cannot see it and cannot get information from it? Because understanding the singularity is central to understanding what a black hole is. A black hole is not just a region of strong gravity. It is a place where space-time itself has been pushed to an extreme, where the equations we use to describe the universe produce results that make no sense, where the distinction between space and time blurs, where the future is not a direction you can point to, but a moment you are falling toward. And if we want to understand the limits of our current theories, the boundaries of what we know, black holes are the place to look. They are the laboratory where general relativity meets quantum mechanics and the two theories clash. The singularity also raises questions about information. If you drop a book into a black hole, that book contains information, the arrangement of atoms on each page, the sequence of letters, the ideas encoded in the text. Classical general relativity says that once the book crosses the event horizon, that information is lost to the outside universe. It falls to the singularity and is destroyed. But quantum mechanics says that information cannot be destroyed. It can be scrambled, spread out, encoded in subtle ways, but the total amount of information in a closed system must remain constant. This is called unitarity, and it is a foundational principle of quantum mechanics. The conflict between general relativity and quantum mechanics on this point is called the black hole information paradox. Stephen Hawking worked on this problem for decades. In 1974, he showed that black holes are not perfectly black. They emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, is thermal, random. It carries no information about what fell into the black hole. If Hawking radiation is the only thing that escapes, and if the black hole eventually evaporates completely by emitting all its mass as radiation, then the information about everything that fell in is lost, destroyed, gone. That conclusion bothered a lot of physicists. It bothered Hawking too, though he initially accepted it. In 2004, he reversed his position and proposed that information might be encoded in the Hawking radiation in subtle ways that classical calculations miss. Others have proposed that information might be stored at the event horizon itself, encoded in the structure of spacetime there. Still others have proposed more exotic solutions involving wormholes, baby universes, or quantum entanglement across the horizon. The paradox remains unsolved, or more accurately, there are multiple proposed solutions and no consensus on which one is correct. The singularity sits at the heart of this debate. If the singularity is a real physical place where information is destroyed, then unitarity is violated and quantum mechanics needs to be revised. If the singularity is not real, if it is replaced by something more complex, then maybe information is preserved in that region and eventually encoded in the outgoing Hawking radiation. Or maybe information is never lost, because the singularity is not a place where information ends, but a place where it is transformed into something we do not yet understand. All of these are possibilities. None of them can be tested directly. Let us go back to the experience of falling. You have crossed the event horizon. You have 17 seconds. The tidal forces are growing. What do you see? What does the universe look like from inside a black hole? This is where things get truly strange, because the geometry inside the event horizon is not like anything you have experienced. The usual rules about space and time no longer apply in the usual way. Directions that pointed outward now point inward. The future, the direction you are moving through time, is literally toward the singularity. And the light reaching you from the outside universe behaves in ways that are hard to visualize. If you looked back toward the event horizon, you would see light from the outside universe compressed into a shrinking circle. All the stars, all the galaxies, everything outside the black hole would appear to be concentrated in a small bright region behind you. This is not because the universe is actually shrinking. It is because spacetime inside the event horizon is so curved that light from the outside takes longer and longer to reach you as you fall inward. The photons are chasing you, falling inward with you, but they are redshifted and distorted by the curvature. The circle of light would grow smaller and dimmer as you fell, until eventually it would fade entirely, not because the universe disappeared, because the geometry of spacetime inside the horizon is such that light from the outside cannot keep up with you. Ahead of you, toward the singularity, there would be darkness, not the darkness of empty space, the darkness of a region where spacetime itself is curved so severely that no light from the outside reaches it. Any light you shine in that direction would be pulled inward faster than it could propagate away from you. You would be falling into a void, a region of space where the future is a physical location you are approaching at an accelerating rate. The singularity itself would not be visible. You could not see it until you reached it, and at that point, seeing it would not matter because you would be part of it, stretched, compressed, torn apart, converted into a stream of particles and energy, falling into a region where space-time curvature becomes infinite and the laws of physics as we know them cease to apply. The final moment would not be dramatic in the way most people imagine. There would be no explosion, no flash of light, no sense of impact. Just an overwhelming tidal force that pulls you apart faster than your nerves could transmit pain signals, and then nothing, or something, we do not know. Here is another way to think about it. Outside the event horizon, space is something you can move through, and time is something that passes. You can choose to move left or right, forward or backward. You cannot choose to move backward in time. Time flows in one direction. Inside the event horizon, the roles of space and time are swapped in a certain sense. The radial direction, the direction toward the singularity, becomes time-like. It is no longer a direction you can move through. It is a direction you are moving through, whether you like it or not, the same way you move forward through time outside the horizon. And time itself becomes space-like in certain coordinates, though this language is slippery and depends on how you set up your coordinate system. The point is that inside the horizon, you cannot avoid moving toward the singularity any more than you can avoid moving toward the next second when you are outside. The singularity is in your future. It is not a place you are traveling to. It is a moment you are approaching. And every second that passes brings you closer. Not closer in space, closer in time. The singularity is when your world line, the path you trace through space-time, ends, when the curvature becomes infinite, when the tidal forces rip apart every structure holding you together, when the equations break down and physics as we know it stops applying. How much does the singularity weigh? That is a strange question to ask, because the singularity is not an object with a measurable size. But all the mass that ever fell into the black hole is, in some sense, concentrated there. For Sagittarius A star, that is 4 million solar masses. 4 million times the mass of the Sun, sitting at a point of infinite density. Except density is mass divided by volume. And if the volume is zero, which is what a point singularity implies, then the density is infinite, infinity again. Another sign that the classical description has broken down. Does the singularity have a temperature, a charge, a spin? These questions do not have clear answers within general relativity. The singularity is not a thermodynamic object. It is not in thermal equilibrium with anything. It does not emit radiation. It does not have a surface you could measure the temperature of. If the black hole has charge, then the singularity in the classical picture would carry that charge. If the black hole is spinning, then the singularity is not a point but a ring, a rotating structure with angular momentum. The Kerr solution, which describes a rotating black hole, predicts a ring singularity rather than a point singularity. The geometry around a ring singularity is even more complex than around a point. There are regions where the curvature becomes infinite, but the tidal forces might not be infinite everywhere. There are coordinate patches where strange things happen, closed time-like curves, paths through space-time that loop back on themselves so that you could, in principle, travel into your own past. Nobody thinks these features are physically real. Most physicists believe that quantum effects or the instability of the rotating geometry would prevent them from forming. But the classical equations allow them, and that is another hint that something is missing. Recent research has started to explore alternatives to the singularity picture. Some models propose that the interior of a black hole might not end in a singularity at all, but in a different kind of geometric structure, a phase boundary, a transition region where space-time changes character. These ideas are speculative and not yet widely accepted, but they reflect a growing awareness that singularities, as predicted by classical general relativity, are probably not the final word. They are placeholders, markers of ignorance, regions where we need new physics. One of the more interesting proposals mentioned in a 2026 report is that the Schwarzschild singularity could be a three-dimensional surface rather than a zero-dimensional point. If true, this would mean that the mass of the black hole is not concentrated at a single point, but spread over a finite, though very small region. The curvature would still be extreme, but not infinite. This proposal is part of a broader effort to find ways to remove singularities from the theory without invoking quantum gravity. Some researchers are exploring whether classical modifications to general relativity, such as including higher-order curvature terms or coupling the geometry to other fields, can smooth out the singularity. Others are looking at whether charge or rotation can stabilize the interior in ways that prevent infinite curvature from forming. The controversy is ongoing. Some physicists argue that singularities are real physical features of black holes and that any attempt to remove them is misguided. Others argue that singularities are mathematical artifacts that will disappear once we have a proper quantum description. The truth is that we do not know, and we will not know until we have a theory of quantum gravity that makes testable predictions. Predictions we can check against observations, but here is the problem. How do you observe the interior of a black hole? You cannot send a probe in and get data back. You cannot see the singularity from outside the event horizon. The event horizon is a one-way information barrier. Whatever happens inside is hidden from the outside universe. The only way to learn about the singularity is to fall in yourself. And if you do that, you cannot report your findings. You can measure, you can record, you can watch your instruments as the tidal forces tear them apart. But the data never leaves, the information never escapes. From the perspective of the outside universe, you are gone, your measurements are gone. Your fate is sealed and unknowable. This is what makes black holes so frustrating and so fascinating. They are the ultimate black boxes, pun intended. You can observe their effects from the outside. You can measure their mass, their spin, their charge. You can watch stars orbit them. You can photograph their shadows, but you cannot look inside. The interior is causally disconnected from the universe you inhabit. It might as well be a different universe. And whatever happens there, whatever the singularity really is, remains one of the deepest mysteries in physics. And yet, the mystery is not entirely opaque, because even though we cannot see inside, we can observe the effects of black holes on their surroundings. We can watch gas spiral inward toward the event horizon, heating up and glowing as it falls. We can measure the gravitational waves produced when black holes merge. We can study the orbits of stars near the galactic center and use them to test general relativity. We can look for signatures of Hawking radiation, though for a black hole as massive as Sagittarius A star, the radiation is far too faint to detect. We can build computer simulations of black hole interiors and see what the equations predict, even if we cannot check those predictions directly. All of these observations and calculations paint a picture, not a complete picture, not a final picture, but a picture of an object so extreme, so beyond everyday experience, that it forces us to confront the limits of what we know. The singularity is the end of that picture, the place where the equations break down, the place where space-time stops being smooth, the place where general relativity hands off to something else, something we have not yet discovered. If you were falling toward the singularity, your final moments would be a race between spaghettification and the limit of your instruments. The tidal forces would grow. Your body would stretch. Your equipment would fail. Your clocks would tick their last ticks. And then you would reach the singularity, or whatever is actually there. A point, a surface, a quantum foam, a region of space-time so warped that the usual concepts of distance and time no longer apply. And at that moment, your world line would end, not in a place, in a time, a moment where the future stops. From outside, none of this is visible. The black hole looks the same whether the singularity is a point, a ring, a surface, or a quantum fuzzball. The event horizon hides everything. It is a perfect censor, preventing the singularity from affecting the outside universe in any measurable way. And that censorship is one of the great unanswered questions in physics. Why does nature hide singularities behind event horizons? Is it a coincidence, or is there a deeper principle at work? A cosmic censorship hypothesis that says singularities are always hidden, always cloaked, always kept out of view. Roger Penrose proposed this idea in 1969. It has never been proven, it has never been disproven, it remains a conjecture. The singularity is the abyss, the place where knowledge ends and speculation begins. It is the final destination for anything that crosses the event horizon, and it is the ultimate test of our theories. If general relativity is correct, the singularity is real. If quantum mechanics is correct, the singularity might not be. Reconciling these two pictures is one of the central challenges of modern physics. And until we do, the center of every black hole remains a mystery. A place we can describe mathematically but cannot understand physically. A place where the universe keeps its deepest secrets locked away behind a horizon of no return. You have fallen into a black hole, watched space-time curve around you, witnessed the event horizon slip past without so much as a bump, and followed your trajectory all the way to the singularity at the center, or whatever is actually there. You have traced the path that light cannot escape from and matter cannot survive. You have reached the point where the equations break down and general relativity hands the story over to something we do not yet have. And now, having followed the journey inward as far as physics allows, the obvious question presents itself. How do we know any of this? How does anyone observe an object that by definition cannot be seen? How do you photograph something that eats light? That question is not rhetorical. It is the central problem of black hole astronomy. And for most of the history of the field, the answer was simple. You do not photograph the black hole. You cannot. You photograph everything around it. You watch the stars orbit an invisible point. You measure the radiation from gas spiraling inward. You track the motion of matter as it accelerates toward the event horizon and glows hot enough to emit X-rays. You build a picture of the black hole by mapping the effects it has on its surroundings, the way you might deduce the shape of a hole in the ground by watching water flow into it. Indirect, clever, effective, but not the same as actually seeing the thing. Until 2022, no human being had ever seen a direct image of Sagittarius A star, not a blurry dot, not an artist's rendering, not a simulation, nothing. We had orbital data, we had mass measurements, we had decades of observations proving beyond any doubt that there was a 4 million solar mass black hole sitting at the center of the Milky Way. But we had never seen it. The black hole itself remained invisible, hidden not by distance or dust or technical limitations, hidden by the laws of physics. Then, on May 12, 2022, the Event Horizon Telescope collaboration released an image. Not an illustration, not a cartoon, a photograph, a direct image of Sagittarius A star, or more precisely, a direct image of its shadow. The dark circle in the center, surrounded by a glowing ring of light. The silhouette of a black hole, captured by instruments spread across the entire surface of the Earth, working together as a single telescope the size of the planet. The image did not show the black hole itself. You still cannot photograph a black hole. What it showed was the absence, the void. The region of space where light goes in and does not come out. The shadow cast by the event horizon against the backdrop of glowing gas swirling around it. And that shadow, that dark circle, was exactly the size and shape that general relativity predicted it would be. 52 microarcseconds across. A microarcsecond is 1/1,000,000th of an arcsecond, which is 1/3600th of a degree. 52 microarcseconds is the angular size of a donut sitting on the moon as viewed from Earth. The fact that we can resolve something that's small, that we can photograph it, that we can measure its diameter to within a few percent, is one of the most remarkable technical achievements in the history of astronomy. Let us back up, because the road to that image took decades. The idea of photographing a black hole's shadow was not new. Theoretical physicists had been calculating what such an image should look like since the 1970s. The predictions were clear. A black hole surrounded by hot glowing gas should appear as a dark circle, the shadow, with a bright ring around it. The ring would be light from the gas, bent and focused by the extreme curvature of spacetime near the event horizon. Some of that light would come from gas on the far side of the black hole, behind the event horizon from our perspective. But spacetime near the horizon is so curved that light from the backside bends around and reaches us anyway, creating a complete ring. The shadow would be about 2.6 times the size of the event horizon itself, because light passing just outside the event horizon can orbit the black hole in an unstable circular path before either escaping or falling in. That region, called the photon sphere, contributes to the size of the shadow. For Sagittarius A star, with an event horizon radius of about 12 million kilometers, the predicted shadow diameter works out to about 31 million kilometers. That sounds large until you account for the distance, 26,000 light-years away. At that distance, 31 million kilometers subtends an angle of about 52 micro-arcseconds. So the question was not whether the shadow existed. The theory said it had to. The question was whether we could build a telescope powerful enough to see it. The resolution of a telescope, its ability to distinguish fine details, depends on two things: the wavelength of light you are observing and the size of the telescope's aperture. Shorter wavelengths give better resolution. Larger apertures give better resolution. The formula is straightforward. The smallest angle a telescope can resolve is roughly the wavelength divided by the diameter of the aperture. For visible light, with wavelengths around 500 nanometers, even a large optical telescope with a mirror 10 meters across can only resolve angles down to about 10 milliarseconds. That is nowhere near good enough. You would need a mirror thousands of kilometers wide to resolve 50 microarcseconds in visible light. Building such a telescope is not feasible. The mirror would collapse under its own weight. And even if you could build it, Earth's atmosphere would blur the image so badly that the resolution would be wasted. Radio waves have much longer wavelengths than visible light. Millimeter wavelengths are about 1,000,000 times longer. That sounds like a disadvantage. Longer wavelengths mean worse resolution. But radio waves have a crucial advantage. They pass through Earth's atmosphere without being absorbed or scattered. And they pass through the dust and gas in the galactic center that blocks visible light. You cannot see Sagittarius A star in visible light. The view is blocked by clouds of interstellar dust sitting between us and the black hole. But in radio wavelengths, the dust is transparent. The black hole is visible, or more accurately, the glowing gas around it is visible. And the shadow cast by the black hole shows up clearly in radio observations. The resolution problem remains. To resolve 50 microarcseconds at a wavelength of 1.3 millimeters, which is the wavelength the Event Horizon Telescope uses, you need an aperture about 10,000 kilometers wide, bigger than Earth. That is where interferometry comes in. Instead of building a single enormous telescope, you build many smaller telescopes and link them together electronically. Each pair of telescopes acts like opposite edges of a single giant mirror. The resolution you achieve is determined by the separation between the telescopes, not the size of each individual dish. This technique is called Very Long Baseline Interferometry, or VLBI. and it has been used in radio astronomy for decades. Here is how it works. Each telescope in the array observes the same target at the same time. The radio waves arriving at each telescope are recorded with precise timing, synchronized to atomic clocks accurate to within billionths of a second. The data from all the telescopes are later combined, correlated, to reconstruct an image. The correlation process looks for patterns in the signals. If the radio waves from the target arrive at two telescopes with a specific time delay, determined by the distance between the telescopes and the direction to the source, the signals will line up when you shift one relative to the other by that delay. By correlating signals from many pairs of telescopes, all observing the same target, you can reconstruct the wavefronts as if you had one giant telescope with an aperture equal to the maximum separation between dishes in your array. The Event Horizon Telescope is a global VLBI network. As of the observations taken in April 2017, the array included 8 telescopes scattered across the planet. The Atacama Large Millimeter Array in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell telescope in Hawaii, the Sub-Millimeter Array in Hawaii, the Large Millimeter telescope in Mexico, the Sub-Millimeter telescope in Arizona, the South Pole telescope in Antarctica, and the Atacama Pathfinder experiment in Chile. Together, these telescopes form a virtual dish about 10,000 kilometers across. Roughly the diameter of Earth, the resolution at 1.3 millimeters wavelength is about 25 microarcseconds, enough to resolve the shadow of Sagittarius A star. The observations are only possible during a brief window each year when the weather is good at all the sites, when Sagittarius A star is visible from most of the array, and when all the telescopes are operational. In April 2017, the Event Horizon Telescope pointed at Sagittarius A star and recorded data for several nights. Each telescope collected more than a petabyte of data per night. A petabyte is 1,000,000 gigabytes. Storing that much data required specialized hard drives, and shipping the drives to a central location for processing was faster than transmitting the data over the internet. The hard drives from the South Pole telescope could not be retrieved until the following Antarctic summer because the station is inaccessible during winter. So the data sat on ice, literally, for months before it could be correlated. Correlating the data took years. The process is not automatic. You cannot just feed the data into a computer and press a button. The raw data are noisy, incomplete, and sparse. VLBI does not give you a complete picture the way a camera does. It gives you a set of measurements, each one corresponding to a specific combination of telescope pairs and observing times. These measurements are called visibilities, and they encode information about the Fourier transform of the image. If you know the Fourier transform, you can reconstruct the image, but the measurements are incomplete. You have visibilities for only the telescope pairs in your array, not for every possible baseline you would need to perfectly reconstruct the image. So you have to fill in the gaps using sophisticated algorithms that guess what the missing data should be, based on assumptions about the structure of the source and the physics of black holes. Multiple teams worked on the reconstruction independently, using different algorithms and different assumptions to make sure the final image was not an artifact of one particular method. All the teams converged on the same basic picture: a bright ring with a dark center, the shadow. The ring had a diameter of about 52 microarcseconds, matching the theoretical predictions to within the measurement uncertainties. The agreement was not approximate, it was exact. The shadow of Sagittarius A star looked exactly the way general relativity said it should. But there was a complication. Sagittarius A star is not a steady, unchanging source. It flickers. The gas swirling around the black hole is turbulent, chaotic, moving at a significant fraction of the speed of light. Bright spots and filaments appear and disappear on timescales of minutes. The observations were taken over several nights, and during that time the source changed. Not dramatically. The overall structure remained the same, but the details shifted. The brightness varied. The position of the bright spots in the ring moved. This variability made the imaging more difficult. If the source had been steady, the reconstruction algorithms would have had an easier time. With Sagittarius A star, the teams had to account for the fact that they were not imaging a single static object. They were imaging a dynamic, evolving system, and the data from different times showed different snapshots of that system. The solution was to treat the observations as a movie, not a photograph. Instead of trying to reconstruct a single image, the teams reconstructed a series of images, each one representing a short time window. Then they averaged those images together to produce a final picture that showed the average structure of the source. The result was the image released in 2022, a ring of light, a dark shadow in the center. The first direct image of the black hole at the center of the Milky Way. Why is the ring bright? Because the gas around the black hole is hot, extremely hot, millions of degrees. Gas at that temperature emits radiation across the electromagnetic spectrum, from radio waves to X-rays. The radiation we see in the Event Horizon Telescope images comes from electrons spiraling around magnetic field lines in the gas, a process called synchrotron emission. The electrons are moving at relativistic speeds close to the speed of light, and their motion generates radio waves. The closer the gas is to the event horizon, the faster it moves, the hotter it gets, and the brighter it glows. The ring is brightest where the gas is densest and hottest, just outside the event horizon. The shadow is dark, not because there is no light there. There is plenty of light. Photons are constantly being emitted by the hot gas everywhere around the black hole. But inside the photon sphere, light cannot escape. It either falls into the event horizon or it orbits briefly before falling in. So when you look at the black hole from the outside, the region inside the photon sphere appears dark. No light from that region can reach you. The shadow is not the event horizon itself. It is larger. It includes the event horizon plus a region just outside where light is trapped in unstable orbits. For a non-rotating black hole, the shadow is 2.6 times the size of the event horizon. For a rotating black hole, the shadow is slightly smaller on one side and slightly larger on the other, because the rotation drags spacetime around the black hole and changes the geometry of the light paths. The Event Horizon Telescope image of Sagittarius A star does not show obvious asymmetry. The ring looks more or less circular. That suggests either that the black hole is not spinning very fast, or that we are viewing it from an angle where the asymmetry is not pronounced. Detailed analysis of the brightness variations around the ring can, in principle, tell us the spin of the black hole and the orientation of its rotation axis. That analysis is ongoing. The data are good enough to constrain the spin, but not yet precise enough to pin it down to a single number. Future observations with more telescopes added to the array will improve the constraints. The image of Sagittarius A star was not the first black hole shadow ever photographed. That distinction belongs to M87 star, the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The Event Horizon Telescope imaged M87 star first, using the same observations from April 2017, and released that image in April 2019. M87 star is much more massive than Sagittarius A star. 6.5 billion solar masses. Its event horizon is enormous, And because it is so massive, the gas around it orbits more slowly. The timescale for variability is longer. The source is more stable. Imaging it was easier, even though it is much farther away. The shadow is physically larger, and the longer variability timescale meant the reconstruction algorithms had an easier time. The M87 star image was historic. It was the first time anyone had photographed a black hole's shadow. It confirmed, beyond any doubt, that event horizons exist. It showed that the shadow had the size and shape predicted by general relativity, and it opened the door to a new era of black hole astronomy. Before that image, we could infer the existence of black holes from their gravitational effects. After that image, we could see them, or see their shadows, which amounts to the same thing. The Sagittarius A star image followed 3 years later, in 2022, and it was harder to obtain, partly because of the variability, partly because of interstellar scattering. Radio waves passing through the ionized gas between us and the galactic center get scattered, blurred, in a way that degrades the image. The scattering is stronger at longer wavelengths. At 1.3 millimeters, the wavelength used by the Event Horizon Telescope, the scattering is just barely tolerable. Observations at longer wavelengths would be even more blurred. Observations at shorter wavelengths would be sharper, but atmospheric absorption makes shorter wavelengths harder to work with. 1.3 millimeters is a compromise, short enough to minimize scattering, long enough to penetrate the atmosphere at high-altitude sites. The Event Horizon Telescope is not finished. The collaboration is planning to add more telescopes to the array. More telescopes mean more baselines, more measurements, better coverage of the visibility plane, and sharper images. There are also plans to extend the observations to shorter wavelengths, where the resolution would be even better and the effects of scattering would be reduced. And there are plans for space-based interferometry. Putting radio telescopes in orbit would allow baselines longer than Earth's diameter. You could achieve resolutions much finer than 25 microarcseconds. You could resolve structure inside the bright ring. You could watch the dynamics of the gas in real time. You could measure the spin of the black hole precisely. You could test general relativity in even stronger gravitational fields, closer to the event horizon. Space-based interferometry is technically challenging. Synchronizing the clocks on widely separated spacecraft is harder than synchronizing clocks on Earth. Transmitting the data back to Earth is harder. Building and launching the telescopes is expensive, but the scientific payoff would be enormous, and several proposals are in development. The next generation Event Horizon Telescope is coming. It will see things we have only imagined. There is another way to observe black holes, and it does not involve light at all. Gravitational waves, ripples in spacetime itself, produced when massive objects accelerate. When two black holes orbit each other and eventually merge, they produce gravitational waves strong enough to be detected on Earth. The waves carry information about the masses and spins of the black holes, the dynamics of the merger, and the properties of the final black hole formed by the collision. Gravitational wave astronomy is a new field. The first detection was made in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Since then, dozens of black hole mergers have been detected. Most of them involve stellar mass black holes, a few to a few dozen times the mass of the Sun. But future detectors, like the planned Laser Interferometer Space Antenna, or LISA, will be sensitive to lower frequency gravitational waves produced by supermassive black hole mergers. LISA will observe black holes like Sagittarius A star and M87 star colliding with each other, events that produce gravitational waves so powerful they shake spacetime across entire galaxies. Gravitational wave observations complement direct imaging. Imaging tells you about the structure of spacetime around a black hole at one moment in time. Gravitational waves tell you about the dynamics of black holes over time, how they move, how they merge, how they radiate energy. Together, these two methods are transforming our understanding of black holes from theoretical curiosities into observable, measurable objects that we can study in detail. The shadow of Sagittarius A star is observational evidence that event horizons exist, that space-time curvature near black holes is exactly what general relativity predicts, that the universe contains regions where gravity is so strong that light itself cannot escape. The image is not just a picture, it is a test of fundamental physics and the theory past. The shadow is the right size, the ring is the right shape, the brightness distribution matches the predictions. Down to the limits of measurement precision, everything fits. But here is what the image does not tell us. It does not tell us what is inside the event horizon. It does not tell us whether the singularity is real or whether quantum effects smooth it out into something else. It does not tell us how Sagittarius A star formed when it formed, or how much it has grown over the billions of years since it first appeared. The shadow shows us the boundary, the edge, the point of no return. Everything beyond that boundary is hidden, and the only way to learn what is inside is to build better theories, theories that merge general relativity and quantum mechanics into a consistent framework. Theories that predict what happens at the singularity and make testable predictions we can check against observations. For now, the shadow is enough. It is proof that we live in a universe where space-time can be curved so severely that entire regions are cut off from the rest of reality, where massive objects can collapse into points of no return, where light itself is trapped and dragged inward by gravity. The black hole is no longer a hypothesis. It is no longer an inference. It is a photograph, a direct image. A shadow cast by an object we can measure, study, and understand, at least from the outside. And that shadow raises the next question. If Sagittarius A star exists now, how did it get here? How did a 4 million solar mass black hole form in the first place? How did it grow? How long has it been sitting at the center of the Milky Way, holding the galaxy together? How long will it remain? These are questions about history, about time, about the life and times of a supermassive black hole, and the answers are stranger than most people expect. You have watched a black hole from the outside. You have traced the geometry of space-time around it, followed the mathematics to the edge of the event horizon, and stared into the abyss where the singularity waits. You have seen the shadow photographed by the Event Horizon Telescope, that dark circle ringed with light, proof that Sagittarius A star is real and sitting exactly where the equations said it would be. But none of that answers the question that should have been nagging at you since the beginning. How did it get there? 4 million solar masses compressed into a region smaller than the orbit of Mercury, sitting at the center of the Milky Way. That did not happen by accident. Black holes do not materialize out of nowhere. They have to form, they have to grow. And the process by which a supermassive black hole like Sagittarius A star came into existence is one of the strangest stories in astrophysics. The problem is time, or more precisely, the lack of it. We know that supermassive black holes existed when the universe was less than 1 billion years old. We have seen them, quasars at redshifts high enough that their light has been traveling toward us for more than 13 billion years. Quasars powered by black holes weighing billions of solar masses. Black holes that massive, that early, should not exist. There simply was not enough time for them to grow by conventional means. Here is why. A black hole grows in two ways. It eats and it merges. When a black hole swallows gas, dust, stars, or any other matter that wanders too close, it gains mass. When two black holes collide and merge, the resulting black hole weighs roughly the sum of the two originals minus a small amount radiated away as gravitational waves. Both processes take time. Eating takes time because there is a limit to how fast a black hole can consume matter. Merging takes time because you need two black holes to find each other, spiral inward and collide. And in the early universe, when the cosmos was less than 1 billion years old, time was the one thing in short supply. The limit on how fast a black hole can eat is called the Eddington limit. It is not a hard barrier, it is a consequence of radiation pressure. When matter falls toward a black hole, it does not fall quietly, it heats up. The gas, swirling inward, forms a disk, an accretion disk, and friction between particles in the disk converts gravitational potential energy into heat, a lot of heat, enough that the disk glows. The closer the gas gets to the event horizon, the hotter it gets, and the more radiation it emits. That radiation pushes outward. Photons carry momentum. When they slam into particles of infalling gas, they exert a force. If the radiation pressure becomes strong enough, it can balance or even overcome the inward pull of gravity. The gas stops falling. The black hole stops eating. The Eddington limit is the accretion rate where the outward radiation pressure exactly balances the inward gravitational pull. For a black hole of a given mass, there is a maximum luminosity it can sustain without blowing away its own fuel supply. And that maximum luminosity corresponds to a maximum accretion rate. Feed the black hole faster than the Eddington rate, and the excess matter gets pushed away by the radiation before it can fall in. The black hole cannot eat it, so the Eddington limit sets a speed limit on growth. For a black hole with the mass of the Sun feeding at the Eddington limit, it takes about 50 million years to double in mass. That is not terrible. Start with a 10 solar mass black hole, the kind you might get from the collapse of a massive star, and let it feed at the Eddington limit for a few 100 million years. You can grow it to a few 100 solar masses. A few billion years, and you could grow it to millions of solar masses. That timeline works fine if you have billions of years to play with. The universe today is nearly 14 billion years old. There has been plenty of time for black holes to grow. But in the early universe, when the first galaxies were forming, the timeline was compressed. The universe was less than 1 billion years old. Some of the quasars we observe at high redshift correspond to black holes that formed when the universe was only a few 100 million years old, and those black holes already weighed billions of solar masses. Run the math backward, and the problem becomes clear. Even if you start with a black hole weighing 100 solar masses, and even if it feeds at the Eddington limit continuously without pause for the entire first billion years of cosmic history, you cannot grow it to 1 billion solar masses. You fall short by a factor of several. The timeline does not close. So how did those early supermassive black holes form? Astrophysicists have spent decades arguing over this question, and the consensus, such as it is, points to a few main possibilities. None of them are entirely satisfying. All of them require conditions that push the boundaries of what we think is possible. The first possibility is that the black holes started out heavier, much heavier. Instead of forming from the collapse of a single massive star, which gives you a black hole weighing a few to a few dozen solar masses, maybe the first black holes formed from the direct collapse of enormous clouds of primordial gas. No stars involved, just gas. A cloud of hydrogen and helium, thousands or tens of thousands of solar masses collapsing under its own gravity straight into a black hole. Skip the star phase entirely. Start with a seed black hole weighing 10,000 or 100,000 solar masses and suddenly the timeline works. Feed that seed at the Eddington limit for a few 100 million years, and you can grow it to 1 billion solar masses. The math closes. This process is called direct collapse, and it is not easy to make happen. Under normal conditions, when a gas cloud collapses, it fragments, breaks apart into smaller clumps. Each clump collapses further and eventually forms a star. You do not get one big collapse, you get a cluster of stars. To form a direct collapse black hole, you need to prevent fragmentation. You need the gas to stay hot and smooth so it collapses as a single coherent mass. That requires very specific conditions. The gas has to be metal poor, meaning almost no elements heavier than helium. Heavy elements cool gas efficiently by radiating energy away. If the gas can cool, it fragments. Primordial gas, the kind that existed in the first few 100 million years after the Big Bang, was almost entirely hydrogen and helium. No carbon, no oxygen, no metals. That helps. But you also need the gas to be heated by something. Radiation from nearby stars. Ultraviolet light that keeps the gas ionized and prevents it from cooling. If the conditions are just right, a massive cloud of primordial gas can collapse directly into a black hole without ever forming stars. Simulations show that this can work. Under the right circumstances, you can collapse a cloud of 100,000 solar masses or more into a black hole in less than 100,000 years. That is fast. Cosmically speaking, that is instantaneous. And if you follow the evolution forward, feeding the resulting black hole with gas funneled in by the gravitational pull of the growing galaxy around it, you can grow it to 1 billion solar masses in a few 100 million years. The timeline fits. The physics, at least in the simulations, works. But direct collapse requires a very specific set of conditions. It probably did not happen everywhere. It probably did not happen often. It might have happened in a few rare regions of the early universe where everything lined up just right. And those rare seeds could have grown into the supermassive black holes we see powering quasars at high redshift. That is one possibility. The second possibility is that the black holes grew faster than the Eddington limit allows. The Eddington limit is not a law of physics. It is a result you get when you assume the accretion flow is smooth and spherically symmetric. Real accretion is messy. The gas does not fall in uniformly from all directions. It comes in clumps, filaments, streams. In some configurations, gas can fall in from directions where the radiation pressure is weaker, bypassing the Eddington barrier. This is called super-Eddington accretion. Simulations show that under certain conditions, particularly during galaxy mergers, gas can funnel into the center of a galaxy at rates far exceeding the Eddington limit. The black hole eats faster than it should. The timeline compresses. A black hole that would take 1 billion years to grow at the Eddington rate might grow in a few 100 million years if it feeds super-Eddington. This idea has gained traction in recent years. Galaxy mergers are chaotic events. When two galaxies collide, their gas clouds slam together, lose angular momentum, and fall toward the center. The result is a flood of fuel dumped into the central region where the black holes sit. During the peak of the merger, the accretion rate can spike. The black hole gorges itself. And if this happens repeatedly, if a growing galaxy goes through multiple mergers in its early history, the central black hole can grow much faster than the Eddington limit would predict. Some simulations suggest that mergers in the early universe could funnel more than 100 million solar masses of gas into the nuclear region in a single event, enough to grow a supermassive black hole in a few 100 million years. The third possibility is a hybrid. Start with a direct collapse seed, a black hole weighing 100,000 solar masses or more. Then grow it through a combination of Eddington and super-Eddington accretion, spiking during mergers and tapering off between them. This pathway combines the advantages of both mechanisms. You get a head start from the massive seed. You get rapid growth during the chaotic early phases of galaxy formation, and you end up with billion solar mass black holes in time to power the high redshift quasars we observe. This is the scenario that most current models favor, not because it is proven, because it is the one that fits the observations best. All of this raises a question. If supermassive black holes formed early and grew fast in the chaotic conditions of the young universe, what is Sagittarius A star doing now? Is it still growing? Is it still feeding? Or has it finished its main course and moved on to dessert? The answer is that Sagittarius A star is currently starving, or close to it. Compared to the quasars that powered the early universe, Sagittarius A star is remarkably quiet. It is not eating much. The accretion rate is tiny, orders of magnitude below the Eddington limit. The radiation it emits is faint. If you pointed an X-ray telescope at the galactic center, you would detect some emission from hot gas near the black hole, but nothing dramatic, no jets, no outbursts, no fireworks. Sagittarius A star is a dormant giant, a black hole that once fed voraciously and is now coasting on fumes. We know it was more active in the past. There is evidence. Bubbles of hot gas, called the Fermi bubbles, extend above and below the galactic plane, stretching for tens of thousands of light-years. These bubbles are thought to be the remnants of a massive outburst from the galactic center, an event that happened a few million years ago when Sagittarius A star swallowed a large clump of gas, or a star, and belched out jets of high-energy particles. The bubbles are still expanding, still glowing faintly in gamma rays. They are a fossil, a trace of a time when the black hole was more active, and there are hints that it might flare up again. In 2019, astronomers observed Sagittarius A star brightening dramatically in the infrared. The brightness increased by a factor of 75 over the course of a few hours, then faded back to normal. The flare was likely caused by a blob of gas spiraling inward toward the event horizon, heating up as it fell, and emitting a burst of radiation before disappearing. Flares like this happen occasionally. They are reminders that the black hole is not completely dormant. It is just idling, waiting for the next meal. The meal comes from the accretion disk, or more accurately, the accretion flow, because the gas around Sagittarius A star is not in a well-defined disk. It is a chaotic soup of hot ionized plasma, magnetic fields, and turbulent eddies. The gas comes from several sources: winds from massive stars near the galactic center, material stripped from stars that pass too close to the black hole, interstellar gas drifting inward from farther out in the galaxy. Most of it does not fall in, it orbits, radiates energy, and drifts away. A small fraction spirals inward, crosses the event horizon, and adds to the black hole's mass. That small fraction is enough to produce the faint glow we see in radio and X-ray observations. Accretion disks are the engines that power not just Sagittarius A star, but every active black hole in the universe. When gas falls toward a black hole, it does not fall straight in. It has angular momentum. It has to shed that angular momentum before it can cross the event horizon. The way it does that is by forming a disk, a flat rotating structure where the gas spirals inward slowly, losing angular momentum through friction with neighboring gas. Friction heats the gas. The inner regions of the disk, closest to the black hole, get hot enough to emit X-rays. The outer regions, cooler and farther out, emit optical and infrared light. The result is a spectrum that peaks in the ultraviolet or soft X-ray, a feature called the Big Blue Bump. That bump is the signature of an accretion disk. It is what makes quasars visible across billions of light years. The luminosity of the disk depends on the accretion rate. Feed the black hole faster, and the disk gets hotter and brighter. Feed it slower, and the disk dims. For a black hole feeding at the Eddington limit, the disk can outshine the entire galaxy around it. That is what we see in quasars. The central black hole, surrounded by a disk of infalling gas, emits so much light that it drowns out the light from the billions of stars in the host galaxy. Point a telescope at a quasar, and what you see is not a galaxy. It is a point of light, brilliant, blinding, powered by gravity converting mass into energy at an efficiency that makes nuclear fusion look wasteful. Quasars are active galactic nuclei, or AGN. The term is broader. It includes not just quasars, but any galaxy with a luminous core powered by accretion onto a supermassive black hole. Some AGN are radio loud. They emit jets, narrow beams of particles and radiation streaming out from the poles of the black hole at close to the speed of light. These jets can extend for millions of light years, far beyond the galaxy itself, lighting up the intergalactic medium and creating enormous radio lobes visible to telescopes on Earth. Other AGN are radio quiet, no jets, just the disk, just the glow of infalling gas. Sagittarius A star, in its current state, barely qualifies as an AGN. It is too faint, too quiet, but it has the same basic machinery. A supermassive black hole, an accretion flow, a faint glow. The difference is scale. The relationship between supermassive black holes and galaxies is one of the tightest correlations in astrophysics. Almost every large galaxy has a supermassive black hole at its center. The mass of that black hole is correlated with the mass of the galaxy's central bulge, the dense spherical region of stars surrounding the nucleus. The correlation is not perfect, but it is close. A galaxy with a bulge mass of 100 billion solar masses will have a central black hole weighing about 100 million solar masses. The ratio is roughly 1 to 1,000. The black hole weighs about 0.1% as much as the bulge. That correlation is remarkable because the black hole and the bulge are very different objects. The bulge is made of stars, billions of them, spread over thousands of light years. The black hole is a point, a singularity hidden behind an event horizon a few light hours across. How do these two objects, so different in structure and scale, end up with masses that track each other so precisely? The answer is that they grew together, co-evolved. The black hole and the galaxy fed off the same reservoir of gas, and the growth of one influenced the growth of the other. Here is how it works. In the early universe, gas clouds collapse to form the first galaxies. As the gas falls inward, some of it funnels all the way to the center, forming a seed black hole. The black hole starts feeding. As it feeds, it emits radiation. That radiation heats the surrounding gas. If the black hole feeds fast enough, the radiation can blow the gas away, clearing out the center of the galaxy and shutting off the fuel supply. The black hole stops growing. The gas drifts outward, cools, and eventually falls back in. The cycle repeats. Feed, blow out, starve, feed again. Over billions of years, the black hole and the galaxy settle into a kind of equilibrium where the black hole grows just fast enough to regulate the gas supply without completely shutting it off. This process is called AGN feedback. It is one of the key mechanisms shaping galaxy evolution. Without feedback, simulations predict that galaxies would be much more massive than they actually are. Gas would cool and collapse efficiently, forming stars at a furious rate, and the result would be galaxies packed with far more stars than we observe. But feedback from the central black hole heats the gas, prevents it from cooling, and slows down star formation. The black hole acts as a thermostat. It regulates the growth of the galaxy by controlling the fuel supply. And in doing so, it locks its own growth to the growth of the galaxy around it. The evidence for this is everywhere. Quasars and AGN are most common at high redshift, when the universe was young and galaxies were forming rapidly. That is when the black holes were feeding most actively. As the universe aged and galaxies matured, the fuel supply dwindled, star formation slowed, AGN became less common. The black holes went dormant. Today, most supermassive black holes, including Sagittarius A star, are quiescent. They are no longer shaping their galaxies, they are coasting, waiting, ready to flare up again if a new supply of gas becomes available. Will Sagittarius A star ever feed again? Probably. In a few billion years, the Milky Way is going to collide with the Andromeda galaxy. The two galaxies will merge. The collision will funnel enormous amounts of gas toward the centers of both galaxies, where Sagittarius A star and Andromeda's central black hole are waiting. The two black holes will spiral toward each other, feeding voraciously as they fall, growing larger and brighter, possibly igniting a quasar phase that will light up the merged galaxy for millions of years. Eventually, the two black holes will collide and merge, forming a single black hole weighing about 100 million solar masses. That black hole will be the new heart of the merged galaxy, a system astronomers have already nicknamed Milkomeda. The merger is not scheduled for another 4 billion years, long after the Sun has expanded into a red giant and consumed the inner planets. Long after Earth, if it still exists, has become uninhabitable. But the black hole will still be there, growing, waiting, shaping the galaxy around it. Supermassive black holes are some of the longest-lived objects in the universe. They do not fade, they do not decay, they do not die. They just grow, slowly, patiently, over timescales that dwarf human history. Over timescales that stretch from the first billion years of the universe all the way to its eventual heat death trillions of years from now. And here is the strange part. For all their influence, for all the energy they radiate, and the gas they heat, and the galaxies they shape, supermassive black holes are tiny. Sagittarius A star weighs 4 million solar masses, but occupies a region smaller than the orbit of Mercury. The Milky Way contains 400 billion stars spread over 100,000 light-years. The black hole is a rounding error, a speck, and yet it is the anchor, the hub, the object that sets the orbital velocities for everything within a few light-years of the center and influences the structure of the galaxy as a whole. Mass matters. Concentration matters. And when you pack 4 million solar masses into a region the size of a solar system, the gravitational influence reaches far. The life and times of Sagittarius A star are the life and times of the Milky Way. The black hole formed early, probably within the first billion years of the galaxy's history. It grew rapidly during the chaotic phase, when gas was abundant and mergers were common. It fed, it radiated, it shaped the distribution of gas and stars in the galactic center. And then, as the fuel supply dwindled, it went quiet. It has been coasting for billions of years, punctuated by occasional flares when a star wanders too close or a clump of gas falls in. It will remain quiet for billions more, until the next major merger, until the next feeding event, until the cycle begins again. This is the story of every supermassive black hole: birth, growth, dormancy, rebirth, repeat. The details vary. Some black holes grow faster. Some form earlier. Some are in galaxies that merge more often, but the broad outline is the same. Black holes and galaxies grow together, locked in a feedback loop that regulates the growth of both. The black hole feeds on the galaxy feeds the black hole. And over billions of years, the two settle into a balance. The relationship is not gentle, it is not harmonious, it is violent, disruptive. The black hole heats gas, drives winds, launches jets, and reshapes the galaxy around it. But it is also essential. Without black holes, galaxies would not look the way they do. Star formation would be unchecked. Gas would cool too efficiently. Galaxies would be denser, brighter, and shorter-lived. The universe would be different, less structured, less stable. The black holes are not just passengers. They are architects, shapers of the cosmic structure we see today. And Sagittarius A star, sitting quietly at the center of the Milky Way, is part of that story. A story that began in the chaos of the early universe and will continue long after the last stars burn out. A story written in the language of gravity, spacetime, and the relentless inward pull of mass collapsing into darkness. The life of a supermassive black hole is not measured in years or centuries. It is measured in epochs, in eras, in the rise and fall of galaxies. And we, sitting on a small planet 26,000 light-years away, are watching one chapter of that story unfold. The quiet phase, the dormant phase, the waiting. But the story is not over, not even close. Because for all we have learned about Sagittarius A star, for all the observations and measurements and images and theories, there are still questions we cannot answer, mysteries we have barely begun to probe. The shadow tells us what the black hole looks like from the outside. It does not tell us what happens on the inside. It does not tell us whether the singularity is real or whether quantum gravity replaces it with something else. It does not tell us where the information goes when matter falls in. It does not tell us whether there are other universes beyond the event horizon or whether space-time itself ends at the singularity. These are not small questions. They are some of the deepest unsolved problems in physics. And the answers, if we ever find them, will reshape our understanding of reality itself. You have followed Sagittarius A star from the outside in. You have watched it warp space-time, bend light into rings, pull stars into ellipses so extreme they complete orbits in less than 2 decades. You have crossed the event horizon in thought, traced the path to the singularity, and stared at the photograph of its shadow, that dark circle surrounded by a glowing ring, proof that the invisible anchor at the center of our galaxy is exactly where the equations said it would be. You have watched the black hole grow from a seed in the early universe, feed during the chaotic phase of galaxy formation, and settle into dormancy as the fuel supply dwindled. You have seen it through the eyes of general relativity, quantum mechanics, and the telescopes we have built to photograph the unphotographable. And now, having followed the story this far, you arrive at the place where the story does not end. It opens, because for all we have learned about Sagittarius A star, for all the measurements and models and images, the most important thing we have learned is how much we do not know. The black hole is not a solved problem. It is not a closed case. It is the front line of physics. The place where our two best theories, general relativity and quantum mechanics, meet and refuse to shake hands. The place where the universe keeps its deepest secrets locked away behind a horizon we cannot cross, and the place where the next century of discovery will be written. Sagittarius A star is not just the anchor of the Milky Way. It is a laboratory, a natural experiment sitting 26,000 light-years away, running continuously, producing data we can observe and puzzles we cannot yet solve. It is a window into regimes of physics we cannot replicate on Earth, a test of theories that have worked everywhere else we have looked, and a reminder that the universe is under no obligation to make sense to us. It will do what it does, and we can watch, measure, theorize, and argue. But the final answers, if they exist, are still out of reach. Let us start with what we know. Sagittarius A star weighs about 4.3 million times the mass of the Sun. Its event horizon has a radius of roughly 12 million kilometers. It sits at the dynamical center of the Milky Way, controlling the orbits of hundreds of billions of stars. It is mostly dormant, feeding on a trickle of gas and dust, emitting faint radiation and flaring occasionally when something falls too close. It has been there for billions of years, probably since the galaxy itself was young, and it will remain there for trillions more, long after the last stars burn out and the universe fades into cold darkness. It is real, it is observable, it is measurable, and it behaves exactly the way general relativity predicts it should. That last sentence is worth pausing on. General relativity, a theory written down in 1915 by a physicist who never imagined we would test it at this scale, predicts the size of the shadow, the precession of orbits, the redshift of light, the bending of trajectories, all of it, to within the limits of measurement precision. The theory works, not approximately, exactly. That is extraordinary, and it should make us deeply uncomfortable. Because general relativity also predicts singularities, regions where space-time curvature becomes infinite, where the equations produce nonsense, where physics as we understand it breaks down completely, and the existence of singularities is a sign that the theory is incomplete. Here is the problem. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric that can be curved and stretched, but never torn or quantized. Quantum mechanics, the other pillar of modern physics, tells us that everything at small enough scales is discrete: particles, energy levels. The fabric of space-time itself, if quantum mechanics applies to it, should not be smooth at the smallest scales. There should be a minimum length below which the classical picture no longer makes sense, a scale where space-time becomes grainy, foamy, uncertain. That scale is called the Planck length. It is about 10 to the minus 35 meters, unimaginably small, far smaller than an atom, far smaller than a nucleus, smaller than anything we can probe with current technology. But at that scale, quantum effects should dominate, and if space-time itself is quantum, then singularities, regions of infinite curvature, might not exist. They might be replaced by something else, something finite, something quantum. We do not have a theory that describes this. We do not have a working theory of quantum gravity. String theory is one candidate. Loop quantum gravity is another. There are others. All of them are works in progress. None of them have been tested experimentally, because the regimes where quantum gravity matters, inside black holes and in the first instant after the Big Bang, are not accessible to experiment. We cannot build a particle collider powerful enough to reach Planck scale energies. We cannot send a probe into a black hole and get data back. So we are stuck with theory and indirect tests. And the indirect tests, so far, have not ruled anything out. They have not confirmed anything either. We are guessing, educated guessing. But guessing, the singularity at the center of Sagittarius A star might not be a point of infinite density. It might be a quantum structure, a region where space-time has a different character, a place where the rules change in ways we cannot yet describe. Some models suggest the singularity is replaced by a bounce, a point of maximum curvature where space-time rebounds and tunnels into another region, maybe another universe. Others suggest it is a surface, not a point, with extreme but finite curvature spread over a small but non-zero volume. Still others suggest the singularity is real and quantum mechanics needs to be revised to account for information loss. All of these are possibilities. None of them can be tested directly. The event horizon hides whatever is inside. No signal can escape to tell us what is actually happening at the center, which brings us to the information paradox. This is the problem that has haunted black hole physics since Stephen Hawking worked out the details of black hole radiation in the 1970s. The paradox goes like this. Drop a book into a black hole. The book contains information, the sequence of words on each page, the arrangement of atoms, the quantum state of every particle. According to classical general relativity, once the book crosses the event horizon, that information is lost to the outside universe. It falls to the singularity and is destroyed. End of story. But quantum mechanics says information cannot be destroyed. This is a foundational principle called unitarity. In quantum mechanics, the total information content of a closed system is conserved. It can be scrambled, it can be spread out, it can be encoded in correlations too subtle to measure, but it cannot vanish. If you know the quantum state of a system at one time, you can, in principle, calculate the state at any other time, forward or backward. The evolution is reversible. Information is preserved. Hawking showed that black holes emit radiation, thermal radiation, random photons produced by quantum effects near the event horizon. This radiation, now called Hawking radiation, carries energy away from the black hole. Over time, the black hole loses mass, it shrinks. Eventually, it evaporates completely, leaving nothing but a faint glow of thermal radiation and no black hole. If the Hawking radiation is truly thermal, truly random, it carries no information about what fell into the black hole. The book is gone. The information is destroyed. Unitarity is violated. That is the paradox. General relativity says information is lost. Quantum mechanics says it cannot be. Both theories have been tested in countless other contexts, and both work. But at a black hole, they clash. One of them has to give, or both of them have to be replaced by something deeper. Something that reconciles the two pictures and tells us what actually happens to information when it crosses the event horizon. The paradox has generated an enormous amount of work, thousands of papers, decades of conferences, proposals ranging from subtle to wild. Some physicists argue that information is not lost. It is encoded in the Hawking radiation in ways that classical calculations miss. The correlations are there, hidden in the quantum entanglement between the outgoing photons. Others argue that information is stored at the event horizon itself, encoded in the structure of spacetime there, and slowly released as the black hole evaporates. Still others propose that the interior of the black hole is not what we think it is. That crossing the event horizon does not take you to a singularity, but to another region of spacetime. Maybe a wormhole, maybe a baby universe, maybe something else entirely. And some argue that information really is lost, that unitarity breaks down at black holes, and quantum mechanics needs to be revised. Hawking himself changed his mind on this. In the 1970s, he argued that information was lost. In 2004, he reversed his position and proposed that information might be encoded in the Hawking radiation after all. He did not provide a detailed mechanism. He suggested that quantum fluctuations near the horizon could imprint information onto the outgoing radiation in ways that were too subtle to see in the original calculation. The proposal was controversial. Many physicists were not convinced. The debate continues. What makes the paradox so frustrating is that it sits at the intersection of black holes, quantum mechanics, and thermodynamics, Three areas of physics that all seem to be telling us something fundamental about the universe, and none of them quite agree on what that something is. Black holes have entropy, a measure of disorder, a measure of how much information is hidden inside. The entropy is proportional to the area of the event horizon, not the volume. That is strange. For most systems, entropy scales with volume. More space, more ways to arrange the particles, more entropy. But for a black hole, the entropy is written on the surface, on the event horizon, as if all the information about what fell in is somehow encoded on the boundary, not in the interior. This idea that the information content of a region is limited by the area of its boundary rather than its volume has led to the holographic principle. The proposal, developed in the 1990s, is that the universe itself might be holographic, that the three-dimensional space we experience is a projection of information encoded on a two-dimensional surface at the edge of the universe. This is not metaphor. This is serious physics, and it has deep connections to string theory and quantum gravity. The holographic principle suggests that black holes are not just objects in spacetime, they are windows into the deeper structure of reality. And Sagittarius A star, sitting at the center of the Milky Way, is one of those windows. None of this is settled. The information paradox remains unsolved. The holographic principle remains a conjecture. Hawking radiation has never been detected. For a black hole as massive as Sagittarius A star, the temperature of the Hawking radiation is about 10 to the minus 14 Kelvin, far colder than the cosmic microwave background. The black hole absorbs more radiation from the universe than it emits. It will not start evaporating for trillions of years, long after the universe has expanded and cooled enough that the background temperature drops below the Hawking temperature. By the time Sagittarius A star starts to shrink, the stars will be gone, the galaxies will be gone. The universe will be a cold, dark expanse of isolated black holes, slowly radiating away their mass over timescales longer than 10 to the 100 years, and even then, we will not be around to watch. So why does it matter? Why spend so much effort on a problem that cannot be tested directly, a phenomenon that happens on timescales longer than the current age of the universe, a paradox that might not have an answer? Because the paradox is telling us something. It is pointing to a gap in our understanding, a place where the theories we have, as successful as they are not enough, and filling that gap is how physics moves forward. Newton's laws worked beautifully for centuries until they did not. Mercury's orbit did not fit. Starlight bent near the sun. The data forced us to revise the theory. General relativity replaced Newton, not because Newton was wrong, but because Newton was incomplete. He was correct in the regime where gravity is weak and speeds are slow. Einstein extended the picture to include strong gravity and high speeds. The same thing will happen with general relativity. It works in every regime we have tested, but it does not work at singularities. It does not work when quantum effects dominate, and that means there is a deeper theory waiting to be found. A theory that includes general relativity and quantum mechanics as special cases. A theory that tells us what actually happens at the center of a black hole and what happens to information when it crosses the event horizon. Sagittarius A star is one of the places we go to look for clues. Not because we can see inside, we cannot, but because the black hole is close enough, massive enough, and well studied enough that we can test the predictions of general relativity to extraordinary precision. We can measure the orbits of stars and check whether they precess the way Einstein said they should. We can photograph the shadow and check whether it has the size and shape the equations predict. We can watch for deviations, tiny discrepancies that might hint at new physics. So far, there are no deviations. General relativity fits, but the precision of the measurements keeps improving. The next generation Event Horizon Telescope will have better resolution. Future space-based interferometers will be able to resolve structure inside the bright ring. We will be able to watch the gas swirl around the black hole in real time. We will be able to measure the spin of the black hole precisely. We will be able to test general relativity in stronger and stronger fields, closer and closer to the event horizon. And maybe, eventually, we will see something that does not fit, a signal that deviates from the predictions. A hint that space-time near the event horizon is more complicated than the classical theory allows. A signature of quantum gravity leaking through, that would be the discovery, not confirming what we already know, finding the place where the theory breaks. There is another mystery lurking in the data, the relationship between black holes and galaxies. The correlation between the mass of the central black hole and the mass of the galaxy's bulge. We know the correlation exists. We have measured it in hundreds of galaxies, but we do not fully understand why it exists. Black holes and galaxies are very different objects. The black hole is a point. The galaxy is a structure spanning thousands of light years. How do they communicate? How does the black hole know how massive the galaxy is? How does the galaxy know how massive the black hole should be? The answer is feedback. The black hole feeds on gas funneled in from the galaxy. As it feeds, it emits radiation. That radiation heats the gas, drives winds, and prevents more gas from cooling and falling in. The black hole regulates its own fuel supply, and in doing so, it regulates the growth of the galaxy. The two grow together, locked in a feedback loop. That is the broad picture, but the details are messy. How does feedback work in different types of galaxies? How does it change over time? How sensitive is the correlation to mergers, to the initial conditions of galaxy formation, to the properties of dark matter? We do not know. And Sagittarius A star, because it is so close and so well studied, is one of the best places to look for answers. The future of black hole research is moving fast. The Event Horizon Telescope is expanding. More telescopes are being added to the array. Observations are being extended to shorter wavelengths. Future space missions will observe black holes in gravitational waves, in X-rays, in gamma rays, across the entire electromagnetic spectrum. The Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from supermassive black hole mergers, events that shake spacetime across entire galaxies. These observations will tell us how black holes merge, how they grow, how they influence their environments. And they will test general relativity in regimes we cannot access any other way. There is talk of sending a probe to the galactic center, not to cross the event horizon. That is still science fiction, but to orbit closer than any current telescope. To measure the environment near Sagittarius A star in detail, to map the magnetic fields, to study the accretion flow, to watch stars as they pass within a few astronomical units of the black hole, where the tidal forces are strong enough to deform them. These missions are decades away, but they are being planned, and the science they will produce will reshape our understanding of black holes, galaxies, and the interplay between the two. And then there are the really wild ideas, wormholes, shortcuts through spacetime connecting distant regions. General relativity allows them. The equations have solutions describing tunnels through spacetime, bridges between black holes, pathways that could, in principle, allow you to travel from one part of the universe to another without crossing the space in between. The catch is that every solution physicists have found requires exotic matter. Matter with negative energy density, something we have never observed, something that might not exist. Most physicists think traversable wormholes are not real. But the possibility is there, encoded in the equations, and it refuses to go away. Some researchers have suggested that the connection between entangled particles in quantum mechanics might be related to wormholes. That entanglement, the strange quantum correlation that allows particles separated by vast distances to behave as if they are connected, might be a kind of geometric connection through spacetime, a tiny wormhole linking the two particles. This idea, called ER equals EPR, connects Einstein-Rosen bridges, the original term for wormholes, with Einstein-Podolsky-Rosen correlations, the original term for quantum entanglement. It is speculative, it is controversial, but it hints at a deep connection between quantum mechanics and the geometry of spacetime. And if true, it would mean that the fabric of spacetime at the smallest scales is stitched together by quantum entanglement, that the geometry we see at large scales emerges from quantum correlations at small scales, that spacetime itself is not fundamental but is built from something deeper. These ideas are not proven, they might be wrong, but they are the kinds of ideas that black holes inspire. Because black holes sit at the boundary of the known, they force us to ask questions we would not ask otherwise. What is spacetime made of? What happens to information? Is the universe holographic? Do singularities exist? Are there other universes beyond the event horizon? These are not idle questions. They are the questions that will define the next century of physics. And Sagittarius A star, the invisible anchor at the center of the Milky Way, is part of that story. Not because it is unique. Almost every large galaxy has a supermassive black hole, but because it is ours, because it is close, because we can study it in detail. Because every time we point a telescope at it, we learn something new about gravity, about spacetime, about the limits of our theories, about the universe itself. There is a sentiment, often expressed, that some things in the universe were never meant to be understood, that black holes, with their event horizons and singularities and information paradoxes, are fundamentally beyond human comprehension, that we should admire them from afar and accept that the interior, the singularity, the final fate of information will remain forever hidden, that the universe has secrets it does not share. That sentiment is wrong. The universe does not care whether we understand it. It is not keeping secrets out of spite. It is not hiding answers to protect us. It is just doing what it does, following the laws of physics, whatever those laws turn out to be. And if those laws include black holes, singularities, quantum gravity, and information paradoxes, then those are the laws we will learn. Not today, maybe not in our lifetimes, but eventually, because that is what physics is, a conversation with the universe. We ask questions by building experiments, making observations, testing theories. The universe answers by showing us what happens. And when the answer does not match our expectations, we revise the question. Black holes were once thought to be impossible, theoretical curiosities that could not exist in nature. Then we found them, we measured them, we photographed their shadows, we watched stars orbit them. We detected gravitational waves from their collisions, and now they are part of the standard picture of the universe. Ordinary objects, common, everywhere. The next generation will do the same with the mysteries that remain. The singularity, the information paradox, quantum gravity. These problems are hard. They are at the edge of what we can currently understand. But edges move, theories improve, observations get sharper, and the problems that seem impossible today become textbook material tomorrow. Sagittarius A star is not the end of the story. It is the beginning, a signpost pointing toward the next layer of reality, a reminder that for all we have learned, the universe is deeper than we thought, stranger than we imagined, and far more interesting than any picture we have drawn so far. The black hole sits there, 26,000 light-years away, pulling stars into ellipses, bending light into rings, hiding singularities behind horizons we cannot cross. And every time we look at it, we see the limits of our knowledge staring back, not as a wall, as an invitation. The universe is under no obligation to make sense, but it does make sense. Or at least, it can be understood well enough that we can predict what will happen, test those predictions, and refine our picture when the predictions fail. That process is slow. It is frustrating. It requires patience, creativity, and a willingness to accept that most of our ideas will turn out to be wrong. But it works. And the black hole at the center of the Milky Way, the monster controlling 400 billion stars, the invisible anchor we have finally learned to see, is proof that it works. We found it, we measured it, we photographed its shadow, and now we are asking what comes next. What lies beyond the veil? What happens at the singularity? What the universe is really made of when you strip away everything but gravity and space-time and the quantum foam underneath. Those answers are out there, waiting, hidden not by intent, but by geometry, and we will find them. Not because the universe wants us to, because we refuse to stop looking. You are orbiting it right now. Every breath you have ever taken, every word you have ever spoken, every moment of your life has happened while you were moving through space at 500,000 miles per hour in a long, slow circle around an object you cannot see. 4 million solar masses, 12 million kilometers wide, 26,000 light-years away, close enough to photograph, too far to ever reach. And pulling on everything within reach with a grip that has not loosened in billions of years. That grip is not a force, it is geometry, the shape of space-time itself, bent into a well so steep that even light falls inward and never climbs back out. And that well, that invisible anchor, is what holds the galaxy together, not by reaching out, not by pulling, just by existing. By sitting there, patient and still, while 400 billion stars trace their orbits around it over timescales longer than human civilization has existed. We found it by watching the things it moves. We measured it by tracking stars that scream past at 5% light speed. We photographed it by linking telescopes across the entire planet and staring at a shadow cast by geometry itself. And what we learned is that the universe, for all its size and complexity and chaos, follows rules. Rules we can write down, rules we can test, rules that work over and over in regimes so extreme that the equations themselves start to crack. Sagittarius A star is not the answer. It is the question. What happens when space-time bends so far it breaks? What happens to information when it crosses a line it can never return from? What happens at the center, where the math stops working and the universe refuses to explain itself? We do not know yet, but the black hole is still there, still waiting, still pulling. And somewhere in that darkness, in the place where light goes to die and time itself points inward, the universe is keeping a secret we have not yet learned to ask about.